A space warship is the largest structure humanity can dream of building, often 5 or 6 kilometers long. It is a true vertical city floating in the void, designed to house 50,000 people for perhaps 100 years of travel. But what really blows the mind isn't the plasma cannons or the energy shields that deflect asteroids. It turns out the hardest part is the reality bubble it needs to create. To travel faster than light. It doesn't actually fly. It warps the universe itself in front of it. If the math for this warp bubble is wrong by just 0.001% dot, the ship doesn't just explode, it can erase itself from existence. How do engineers even begin to design a machine that needs to break the fundamental rules of reality? Prepare to fall asleep while listening to this video. Subscribe to the channel, leave your like, and comment what part of the world you are watching from. Get comfortable and relax. Let's begin. Have you ever wondered why we haven't built starships that can zip across the galaxy like in science fiction? The reality is that building a spacecraft capable of faster-than-light travel through space warp bubbles is incredibly complex. In fact, it represents one of the most challenging engineering problems humanity could ever attempt to solve. The physics behind space warp bubbles challenges our fundamental understanding of the universe. According to Einstein's theories, nothing can travel faster than light within space-time itself. However, theoretical physicists have proposed that we might be able to bypass this limitation by warping space-time around a vessel. Imagine creating a bubble of altered reality where space contracts in front of the ship and expands behind it, effectively moving the bubble through space faster than light, while the ship inside remains technically stationary. The mathematics required to describe this process involves calculations across 11 dimensions that push well beyond our current understanding of physics. Teams of theoretical physicists would need to work for decades to refine equations that must be perfect down to the 10,000th percentile. A single rounding error in these calculations could potentially transform the ship into an instantaneous black hole. The energy requirements for creating and sustaining a warp bubble are astronomical in the most literal sense. Current estimates suggest we would need to harness energy equivalent to the mass of Jupiter to create a small warp field. And that's assuming perfect efficiency. The manipulation of negative energy necessary to create the warp bubble requires exotic materials that currently exist only in theory. Scientists speculate about the potential of creating exotic matter with negative mass or energy density, but manufacturing such substances remains far beyond our technological capabilities. The closest concept we have is the Casimir effect, which demonstrates how quantum fluctuations can create a small region of negative energy density between two plates. But scaling this up to spacecraft size presents enormous challenges. Material science faces equally daunting hurdles. The structural components would need to withstand forces never before encountered by human-made objects. The boundary between normal space and the warped space around the bubble would create shear forces capable of tearing apart any known material. Engineers would need to develop entirely new composite materials with properties that seem magical by today's standards. These materials would need to maintain molecular cohesion, while parts of them experience different laws of physics than other parts. The computational systems needed to monitor and adjust a warp bubble would dwarf anything created thus far. Quantum computing systems would need to make constant real-time adjustments to prevent catastrophic collapse of the bubble. These computers would perform calculations so complex that simulating warp bubble dynamics consumes more computational resources than all other engineering simulations for the ship combined. The artificial intelligence required to oversee these systems would need to process information and make decisions faster than human neurons could ever fire. Stability presents perhaps the most terrifying challenge. A warp bubble exists in a precarious state of quantum equilibrium. Any perturbation from external forces, like interstellar dust, radiation, or gravity wells, could cause the bubble to become unstable. When dealing with the fabric of space-time, instability doesn't just mean system failure. It means potentially catastrophic consequences ranging from immediate ship destruction to exotic outcomes like temporal displacement or creating micro-black holes. The control systems would need to anticipate and correct for disturbances across the entire electromagnetic spectrum while accounting for gravitational influences from distant celestial bodies. Navigation through warped space introduces complications that make conventional space travel seem simple by comparison, when your vessel bends reality around itself. Traditional sensors become unreliable at best and useless at worst. Light itself behaves differently at the boundary of the warp field, making optical observation distorted. Mapping safe routes through three-dimensional space that is constantly in motion requires predictive models spanning thousands of light years. The navigation system must consider not just where celestial bodies are when the journey begins, but where they will be when the ship arrives, requiring gravitational models of near-perfect precision. Microscopic deviations in the initial trajectory amplify exponentially, potentially resulting in errors of millions of kilometers at the final destination. Environmental effects of warp travel present another layer of complexity. The boundary between normal space and warped space creates intense radiation that would be lethal to any crew without substantial shielding. The very process of compressing space in front of the ship would concentrate cosmic radiation to dangerous levels. Additionally, theoretical models suggest that particles in normal space encountered by the leading edge of a warp bubble would be captured and accelerated to relativistic speeds, creating a deadly particle beam that would be released when the warp field collapses at the destination. Perhaps most concerning are the unknowns, the effects we cannot predict because they emerge from physics we don't yet understand. Some theories suggest that warp travel might create closed time-like curves, effectively enabling time travel with all its paradoxical implications. Others propose that sustained warp fields might thin the boundary between our universe and hypothetical parallel dimensions, with unpredictable consequences. Despite these immense challenges, researchers continue theoretical work on warp physics. Small-scale experiments with quantum optics and metamaterials aim to create tiny distortions in space-time that might one day lead to breakthrough understandings. While a functioning warp ship remains firmly in the realm of science fiction for now, the pursuit of such technology drives advancement in numerous fields, from theoretical physics to material science. The journey toward faster-than-light travel may be the greatest engineering challenge humanity will ever undertake. But each small step forward expands our understanding of the fundamental nature of our universe. Number sign life support systems for centennial missions. Imagine being born, living your entire life, and eventually dying aboard a spacecraft traveling between stars. This scenario isn't just science fiction, it's the reality that would face multiple generations of humans on any interstellar mission using sublight propulsion. Creating life support systems capable of sustaining thousands of people for 100 years or more in the void of space represents one of the most complex engineering challenges imaginable. The scale of the problem is mind-boggling. A centennial mission requires creating a completely self-contained biosphere that can operate without any external inputs for decades. Unlike the International Space Station, which receives regular resupply missions, an interstellar vessel must recycle virtually 100% of its resources. This challenge goes far beyond simply having enough oxygen and water. It requires perfectly replicating Earth's biogeochemical cycles in a closed system. Air recycling forms the foundation of any long-duration life support system. Humans consume oxygen and produce carbon dioxide, creating a cycle that must be perfectly balanced. Current space station technology uses mechanical carbon dioxide scrubbers that need regular maintenance and replacement parts. For a centennial mission, engineers would need to develop systems that are either completely self-maintaining or so redundant that they could continue functioning despite component failures. Biological systems offer one solution. Carefully designed plant habitats could absorb carbon dioxide and release oxygen through photosynthesis. But these would need to be precisely balanced with the crew's respiration. Some designs incorporate genetically engineered algae that can produce oxygen more efficiently than natural plants while requiring less space and light. Water reclamation presents an even more crucial challenge. The human body requires water daily, not just for drinking, but for hygiene, food preparation, and countless other uses. Even with ultra-efficient recycling systems, small losses accumulate catastrophically over a century. Engineers must develop water purification systems that achieve an efficiency of 99.9999%, recovering even the moisture from exhaled breath and the water vapor released through skin. Multi-stage filtration, combining mechanical, chemical, biological, and even molecular separation would be needed to ensure water remains potable through countless recycling cycles without accumulating contaminants or pathogens. Food production for a century-long voyage requires agricultural systems that can operate indefinitely without external inputs. Hydroponic and aeroponic farming offers efficient use of limited space, but these systems are notoriously complex and vulnerable to failures. For true sustainability, food systems would need redundancy across 7 different levels, each capable of sustaining the entire population if other systems fail. This might include traditional crop cultivation, single-cell protein production, insect farming, fungal-based foods, and synthetic nutrient manufacturing. The nutritional diversity must be carefully balanced to prevent deficiencies over generations, which means maintaining viable seed stocks and preventing genetic drift in crop species throughout the journey. Waste management in a closed system isn't just a sanitation issue, it's essential for resource recovery. Every atom brought aboard the ship at launch must be continuously reused throughout the mission. Human waste, food scraps, expired materials, and even the bodies of the deceased must be processed to recover water, organic compounds, and minerals for recycling back into the life support system. Advanced decomposition systems using specialized microorganisms would break down complex organic materials into their constituent elements, ready to be incorporated back into the food production cycle. Microbiological control presents a uniquely complex challenge for centennial missions. The ship's environment must maintain the beneficial microbiome that humans require for health while preventing the proliferation of pathogens. Over decades, microbial populations will evolve and adapt to the closed environment, potentially becoming more virulent or developing resistance to control measures. Biological monitoring systems would need to continuously analyze the ship's microbiome, identifying concerning changes before they become problematic. This balancing act requires maintaining enough microbial diversity for healthy human life while controlling potentially dangerous evolutionary paths. The psychological aspects of environmental design are just as important as the physical elements. Humans evolved in open spaces with natural light cycles, weather patterns, and changing seasons. The artificial environment of a generation ship must simulate these conditions closely enough to prevent psychological deterioration over decades of confinement. Research in isolated environments like Antarctic research stations has shown that humans require sensory variety, natural elements, and the illusion of open space to maintain mental health. Engineering solutions might include vast internal spaces with artificial skies, programmable weather systems, and simulated day-night cycles that provide the environmental cues humans evolved with. Perhaps the most daunting aspect of centennial life support is the inevitable aging and failure of physical components. Every pump, filter, dot, fan, sensor, and computer system has a finite lifespan, typically measured in years rather than decades. A 100-year mission would require either components built to last several times longer than anything currently manufactured, or more realistically, period, the capability to fabricate replacement parts on board. This means the ship must carry not just spare parts, but entire manufacturing facilities capable of producing everything from simple mechanical components to complex electronic systems. These facilities would themselves require maintenance and replacement over time, creating a nested problem of sustainability. Temperature regulation throughout the massive structure of an interstellar ship presents its own challenges. The side facing the stars might absorb tremendous heat while the opposite side radiates into the void of space, creating temperature differentials that could stress structural components and life support systems. Heat distribution systems must transport thermal energy efficiently throughout the vessel while radiating excess heat into space. The energy used for temperature control alone would dwarf the power requirements of many modern cities. Radiation protection for centennial voyages goes beyond the relatively simple shielding needed for short-duration missions. Over decades, even low-level cosmic radiation accumulates, potentially causing increased cancer rates, fertility problems, and even genetic damage that could be passed to subsequent generations. Shielding an entire habitat against cosmic radiation requires massive amounts of material, water, soil, or dedicated shielding compounds, adding substantially to the vessel's mass. Some designs propose surrounding the habitable areas with water reservoirs that serve dual purposes as both radiation shields and life support resources. The interconnected nature of these systems creates compounding complexity. A problem in one system inevitably affects others. A failure in temperature regulation might stress food production, which reduces oxygen generation, which impacts crew health, which decreases maintenance capability, and so on in a potentially catastrophic cascade. This interconnectedness requires holistic design approaches that consider the life support system not as separate components, but as a single integrated organism with complex feedback loops and dependencies. Creating life support for centennial missions represents the ultimate test of our understanding of ecological systems and sustainable engineering. While the challenges seem overwhelming, they also drive innovation in fields ranging from bioengineering to materials science. Each advancement brings us one step closer to the stars, extending humanity's reach beyond our solitary world toward a future among the stars, beyond the complex physical systems required to support life in space. The human element introduces equally significant challenges. Designing a functional society that will remain isolated for generations requires social engineering on an unprecedented scale. Building a stellar city isn't just about creating physical infrastructure, it's about crafting a complete human civilization that can thrive in isolation for centuries. The governance systems needed for an interstellar spacecraft differ fundamentally from any political structure we've developed on Earth. Traditional models of democracy might prove inefficient for rapid decision-making in crisis situations, while authoritarian structures risk becoming oppressive over generations. Most designs propose hybrid systems with distributed decision-making for daily operations, but centralized authority for emergencies. The governance structure must balance stability with adaptability, allowing enough flexibility to address unforeseen challenges while maintaining consistent leadership through generations. Some proposals include AI-assisted decision systems that provide objective analysis of complex situations, though final authority typically remains with human leadership councils representing different ship sections and specializations. Conflict resolution becomes critically important in an environment where people cannot simply walk away from disagreements. In a closed system with limited space, unresolved conflicts could escalate into factions that threaten the entire mission. Specialized mediation systems would be essential, with trained conflict resolution specialists holding positions of high importance in the social structure. Many designs incorporate mandatory mediation protocols that engage before conflicts reach critical levels, with the understanding that harmony isn't optional in an environment where everyone's survival depends on cooperation. The justice system would likely focus on rehabilitation and community service rather than punitive measures, as removing productive members from society through incarceration would strain already limited resources. Education systems aboard interstellar vessels face the monumental task of preserving the entirety of human knowledge while training successive generations in the specialized skills needed to maintain the ship, unlike Earth-based education that can specialize across different institutions. The ship's educational system must produce experts in every field necessary for survival, from nuclear engineering to medicine to agriculture. knowledge preservation becomes particularly critical as information not actively taught can be lost within a few generations. Historical records show that specialized knowledge can disappear surprisingly quickly when not practiced regularly. The educational system would likely combine immersive virtual learning environments with practical apprenticeships, ensuring both theoretical knowledge and hands-on skills transfer between generations. Managing genetic diversity presents another crucial challenge for multi-generational missions. A founding population of even several thousand individuals will experience genetic bottlenecking without careful management. Advanced genetic screening and planned reproduction might be necessary to prevent dangerous recessive traits from becoming prevalent in the population. This raises complex ethical questions about reproductive freedom versus collective survival. Most proposed systems involve voluntary genetic counselling with strong cultural emphasis on genetic diversity rather than strictly enforced reproductive policies. The goal isn't genetic engineering for enhancement, but ensuring population health over many generations of closed-system reproduction. The psychological challenge of maintaining cultural identity and purpose across generations cannot be overstated. The first generation of crew members chose their mission and understand Earth as their ancestral home. For subsequent generations born on the ship, Earth exists only in records and stories. These individuals might question why they should maintain systems and traditions established by ancestors for a mission they never chose. Creating meaningful cultural narratives that provide context and purpose for shipborne generations becomes essential for long-term mission success. Cultural anthropologists suggest that unique traditions, rituals, and observances would naturally evolve, creating a distinct ship culture that reinforces the collective mission while acknowledging the reality of life in space. Family structures would likely evolve beyond Earth's traditional models to adapt to the unique environment. Extended family networks might become the norm, with child-rearing responsibilities shared among multiple adults to distribute the educational burden and create stronger social bonds. Some proposed systems include sectional families, where children form bonds with adult mentors throughout different ship sections, ensuring knowledge transfer across specializations and creating redundancy in case biological parents become unavailable through accident or illness. These adaptive family structures would help ensure that children receive diverse perspectives and skills while strengthening community cohesion. Population control represents one of the most sensitive but critical aspects of stellar city planning. Resources aboard even the largest conceivable vessels remain finite, requiring careful balance between birth and death rates. Most designs incorporate cultural systems that normalize small families, with reproduction rights perhaps tied to retirement or death of other crew members. Such systems would need to be perceived as fair and necessary rather than oppressive to avoid rebellion in later generations. Anthropologists suggest that ship-borne generations might naturally develop different attitudes toward reproduction than Earth cultures, viewing population balance as a fundamental aspect of their closed ecosystem rather than a restriction on freedom. Recreation and leisure become surprisingly important for long-duration missions. Humans require not just physical sustenance but meaningful activities that provide purpose and enjoyment. Sports adapted for ship environments, artistic pursuits, and virtual reality experiences would all play crucial roles in maintaining psychological health. The ship's design would likely include dedicated recreational spaces that can be reconfigured for different activities, providing environmental variety that helps prevent sensory monotony. Games and competitive activities would evolve to reinforce skills relevant to ship operations, naturally blending recreation with practical education through cultural evolution. Religious and philosophical systems would inevitably transform in the isolated environment of an interstellar vessel. Earth-based religions might evolve into unique forms that incorporate the reality of space travel and closed-system living. New belief systems might emerge that sacralize the mission itself or the vessel as a living entity that sustains the community. These evolving belief systems would play crucial roles in providing meaning and ethical frameworks for shipborne generations. Sociologists suggest that successful stellar societies would neither suppress nor rigidly preserve religious traditions, instead allowing adaptive evolution of belief systems that support community cohesion and psychological well-being. The social psychology of space travel over generations requires addressing what specialists call horizon hunger, the human need for new experiences and frontiers. Earth-based humans satisfy this through travel, career changes, or moving to new locations, options unavailable in a closed vessel, virtual reality environments, rotating living assignments between ship sections, and scheduled major social reorganizations could help address this fundamental human drive. Creating the perception of novelty and opportunity within a physically limited environment represents one of the most subtle but important aspects of stellar city design. Getting all these elements right could mean the difference between a thriving interstellar society that reaches its destination with a healthy, capable population, or a failed mission where social breakdown proves more dangerous than any technical malfunction. The success of multi-generational space travel may ultimately depend less on engineering prowess than on our ability to design human systems that remain stable and adaptable across centuries of isolation among the stars. The journey between star systems requires navigation capabilities far beyond anything developed for conventional space travel. Interstellar navigation and advanced astrocartography present unique challenges that must be overcome for successful missions spanning decades or centuries. While engineering problems like propulsion and life support receive more attention, finding your way across light years of space proves equally formidable. The fundamental challenge of interstellar navigation stems from the vast scales involved. The distance to even the nearest star system, Alpha Centauri, DOT, spans more than 4 light-years, approximately 25 trillion miles. At these distances, even microscopic errors in trajectory calculations amplify exponentially. A course deviation of just 100,000th of a degree near our solar system could result in missing a target star system entirely after a journey of several light-years. This requires unprecedented precision in both initial course calculations and continuous adjustments throughout the journey. Traditional celestial navigation methods used by early space missions become inadequate for interstellar travel. Within our solar system, spacecraft can triangulate their position using known objects like the Sun and planets. In interstellar space, these reference points become distant and impractical for precise positioning. Instead, interstellar vessels would rely on mapping distant quasars and pulsars, extremely bright galactic nuclei, and rapidly rotating neutron stars that emit regular radio pulses. These objects function as cosmic lighthouses, providing fixed reference points against which a ship can determine its position with remarkable accuracy, despite being thousands or millions of light-years away. The dynamic nature of space introduces additional complications. While we perceive stars as fixed points in the sky, they actually move through space at considerable speeds. During a voyage lasting decades, the destination star system will have moved significantly from its position at launch. Accurate navigation requires modelling not just where celestial bodies are at departure, but where they will be upon arrival. This demands gravitational models of extraordinary precision that account for the movements of thousands of stars and their complex gravitational interactions over decades. These calculations must incorporate relativistic effects that become significant at the speeds necessary for interstellar travel. Real-time course correction presents another layer of complexity. Any interstellar mission must contend with the interstellar medium, the gas, dust, and plasma that fill the seemingly empty space between stars, while extremely diffuse by Earth standards. This material can cause meaningful course deviations over light-years of travel. More problematically, DOT. The distribution of this material isn't uniformly mapped and can change as stellar winds and supernova remnants create new density patterns. Quantum radar systems would need to detect these anomalies at incredible distances to allow for course recalculations, with sensitivity far beyond current technology. The mapping of warp streams, Regions where space-time is naturally more flexible due to the gravitational influence of massive objects becomes crucial for energy-efficient travel. These natural highways through space could allow vessels to reduce energy consumption by riding gravitational currents, similar to how aircraft use jet streams in Earth's atmosphere but operating according to the principles of general relativity rather than fluid dynamics. Identifying and utilizing these pathways requires three-dimensional mapping of space-time curvature with sensitivity to distortions measured in fractions of a proton's width. For vessels using warp technology, navigation faces additional unique challenges. The very bubble of warped space-time surrounding the ship distorts observations of the external universe. Light entering this distorted region follows curved paths, creating complex optical illusions that must be mathematically corrected to obtain accurate positional data. The navigation system must constantly adjust for these distortions, which themselves change based on the warp field's intensity and configuration. Some theoretical models suggest creating navigation windows, regions of the bubble specifically configured to minimize distortion for observation purposes. Emergent hazards represent another navigation concern. Rogue planets ejected from their star systems drift through interstellar space without emitting light, making them extremely difficult to detect until relatively close. Primordial black holes, theorized to exist from the early universe, would be nearly impossible to observe directly until dangerous proximity. Clouds of dark matter could potentially influence a vessel's trajectory through gravitational effects while remaining invisible to conventional sensors. These hazards necessitate sophisticated detection systems combining gravitational mapping, neutrino detectors, and dark matter sensors to identify dangerous regions before plotting courses through them. Communication limitations compound navigation difficulties. While a vessel might detect a hazard or determine a necessary course correction, communicating with Earth for assistance would be impossible in practical terms. Radio transmissions would take years to reach home, with an equal time for responses to return. This communication delay means interstellar vessels must navigate with complete autonomy, carrying sufficient computational power and decision-making capability to address any navigational challenge without external assistance. The computational requirements for interstellar navigation exceed any current system by orders of magnitude. Simulating the gravitational interactions of thousands of stellar bodies over decades while calculating optimal trajectories through four-dimensional space-time requires quantum computing capabilities that can perform calculations in parallel across multiple probability states. Some theoretical models suggest that true interstellar navigation computers might need to perform calculations by directly manipulating the quantum fabric of reality rather than through conventional binary operations. Time synchronization across vast distances introduces another level of complexity. Einstein's relativity tells us that time passes differently depending on gravitational fields and relative velocity. A ship traveling at significant fractions of light speed experiences time dilation. Time passes more slowly aboard the vessel than for observers on Earth. Navigation systems must maintain precise time synchronization despite these relativistic effects, as even microsecond discrepancies can lead to navigational errors spanning millions of miles at interstellar scales. Quantum entangled chronometers might provide a solution, maintaining perfect synchronization regardless of separation distance. The psychological aspect of navigation cannot be overlooked. Human minds evolved to understand distances measurable in miles or kilometers, not light years. Plotting courses through three-dimensional space over multi-year timeframes exceeds our intuitive comprehension. Advanced visualization systems would be necessary to represent navigational data in forms human operators can meaningfully understand and interact with. These might include immersive holographic displays that compress vast distances into comprehensible scales while preserving the critical relationships between celestial bodies and potential courses. Despite these immense challenges, establishing reliable interstellar navigation capabilities represents an achievable goal with sufficient technological development. Each obstacle drives innovation in fields ranging from quantum computing to gravitational physics. The ancient human dream of navigating by the stars takes on entirely new meaning when those stars become not just guides but destinations in humanity's greatest voyage of exploration. Navigating the vast distances between stars is only possible with incredible amounts of energy. The power requirements for interstellar travel represent one of the most significant technological hurdles humanity would need to overcome before launching a true starship. Energy management for space warp technology demands innovations that push well beyond our current understanding of physics and engineering. The energy needed to create and maintain a warp bubble exceeds the current annual energy production of our entire planet. Conservative estimates suggest that even a modest warp field capable of enveloping a spacecraft would require power equivalent to converting the entire universe's entire mass of Jupiter into pure energy. This fundamental energy challenge means that conventional power sources like nuclear fission or even standard fusion would be woefully inadequate. Engineers would need to develop antimatter fusion hybrid reactors of at least 10th generation sophistication to have any hope of generating sufficient power. Antimatter represents the most energy-dense fuel theoretically possible, releasing energy through perfect matter antimatter annihilation with 100% mass-to-energy conversion efficiency. However, the challenges of antimatter production and storage are immense. Current antimatter production rates in our largest particle accelerators would require tens of thousands of years to produce enough fuel for a single interstellar journey. Any practical starship would need to incorporate its own antimatter production facilities, likely powered by massive solar collectors deployed during the initial phases of the journey while still near a star. Storing this antimatter presents equally daunting obstacles. Since antimatter annihilates upon contact with regular matter, it must be contained without physically touching any part of its storage container. Current experimental antimatter traps use electromagnetic fields to suspend tiny amounts of antimatter in vacuum. But scaling this up to starship quantities would require perfect containment without a single failure for decades. The energy density of antimatter means that even a microscopic containment breach could release energy equivalent to multiple nuclear weapons, potentially destroying the entire vessel. Superconductors would form the backbone of the ship's power distribution network, moving enormous quantities of energy throughout a structure potentially spanning 6 kilometers in length. Unlike conventional superconductors that require temperatures near absolute zero, starship power conduits would need to operate reliably across varying temperature conditions for a century without degradation. The development of room temperature superconductors that maintain perfect conductivity even when exposed to the intense radiation and electromagnetic fluctuations of interstellar space represents a significant materials science challenge. Thermal management presents another critical energy concern. The laws of thermodynamics dictate that no energy system is 100% efficient. Some energy inevitably converts to waste heat. For systems generating power measured in yottawatts, 10 to the 24th power watts, even fractional inefficiencies create enormous heat that must be dissipated. In the vacuum of space, radiative cooling is the only option, requiring massive radiator arrays that would make the ship distinctive visible at interstellar distances. These radiator systems themselves become vulnerable points in the ship's design, as damage to cooling systems could lead to catastrophic overheating within minutes. The containment shields for the primary reactors represent perhaps the most critical safety system aboard. These shields must contain temperatures reaching hundreds of millions of degrees, hotter than the core of most stars. The material science challenges are immense, requiring composite metamaterials that can withstand not just heat but intense neutron flux, gamma radiation, DOT, and the electromagnetic stresses of containing a matter-antimatter reaction. These materials would need to maintain structural integrity without significant degradation for a century of continuous operation. Quantum synchronization between different power systems introduces yet another layer of complexity. The warp field itself is extraordinarily sensitive to power fluctuations, requiring perfect synchronization between multiple reactor systems. Power oscillations must be held to tolerances measured in femtoseconds, millionths of a billionth of a second, to prevent resonance effects that could destabilize the warp bubble. This level of precision requires quantum-entangled control systems operating at speeds that make light seem sluggish by comparison. Energy storage presents its own unique challenges, while the main propulsion systems require continuous massive power. The ship must also maintain reserves capable of powering essential systems for decades if the main reactors need to be shut down for maintenance or emergencies. Quantum battery technology, still in theoretical stages today, would need to be perfected, allowing energy to be stored in the fabric of space-time itself rather than in physical materials with their inherent limitations. The sheer complexity of these energy systems necessitates artificial intelligence management beyond human capabilities. Even with crews trained for decades, human operators could not possibly monitor and adjust the millions of parameters required to maintain optimal energy flow throughout the vessel. AI energy management systems would need to predict and compensate for fluctuations before human operators could even detect them, operating with limited human oversight for routine operations while maintaining the capability to alert crews to emerging problems that require intervention. Redundancy becomes a fundamental design principle when dealing with systems that cannot fail even once during a century-long mission. Primary power systems would need at minimum quintuple redundancy, with each backup system capable of independently maintaining critical functions. This multi-layered approach significantly increases the mass and complexity of the vessel, but represents the only way to ensure sufficient reliability for systems where failure means mission loss and crew death. Perhaps most challenging is the need for these incredibly complex energy systems to operate continuously while undergoing repairs and modifications. Unlike terrestrial power plants that can be shut down for maintenance, many Starship systems must remain operational at all times. This requires designing modular components that can be replaced while systems remain active, similar to replacing parts in a car engine while it's running, but with stakes measured in thousands of lives and trillions of dollars of irreplaceable technology. The technological hurdles in energy management for warp travel are so significant that some physicists argue they represent a fundamental barrier, perhaps explaining why we haven't detected evidence of interstellar civilizations despite the billions of potentially habitable planets in our galaxy. Any species capable of overcoming these energy challenges would have mastered physical principles that appear magical by our current scientific understanding. Even if a civilization managed to solve the enormous energy production and management challenges of interstellar travel, they would immediately face another critical issue: how to protect their trillion-dollar investment and irreplaceable crew from the myriad threats lurking in interstellar space. Defense systems and energy shields represent a crucial aspect of Starship design that's often overlooked in discussions focused on propulsion and life support. The first line of defense for any interstellar vessel is its energy shield system, which must protect against threats ranging from microscopic dust particles to directed energy weapons. While the concept might seem familiar from science fiction, the engineering reality is far more complex. At relativistic speeds, even individual hydrogen atoms in interstellar space carry kinetic energy equivalent to small tactical nuclear weapons. A comprehensive shield system must detect and deflect particles ranging from subatomic to centimeter-sized, any of which could cause catastrophic damage through kinetic impact alone. These shields would likely combine multiple technologies operating in synchronized layers. The outermost defense would be electromagnetic deflection fields, extending kilometers beyond the physical hull, gently pushing charged particles away from the vessel's path. For larger or neutral particles, laser arrays would vaporize approaching objects, converting solid threats into plasma that can then be deflected by the electromagnetic fields. The innermost layer would be physical shielding incorporating self-healing metamaterials capable of instantly repairing micrometeoroid impacts without compromising structural integrity. The materials science required for the physical shield layer represents a significant challenge in itself. Current experimental self-healing materials can repair minor damage, but Starship shield materials would need to recognize damage patterns. respond intelligently to different types of impacts, and rebuild themselves atom by atom while under continuous stress. These metamorphic materials would incorporate billions of microscopic sensors and repair mechanisms, effectively creating an outer skin that functions as both armor and immune system, beyond natural hazards. Any interstellar civilization must consider the possibility of encountering other intelligent species, potentially with unknown and hostile capabilities. Electronic countermeasure systems would need to anticipate technologies that might have evolved during the century-long mission duration or been developed by other civilizations with different technological paths. These systems would combine quantum encryption, signal analysis artificial intelligence, and adaptive jamming capabilities to protect against everything from cyber attacks to sensor disruption attempts. The defensive artificial intelligence represents perhaps the most sophisticated computer system aboard. When potential attacks occur at distances where light-speed communications would take minutes to reach human operators, the defense AI must make life or death decisions independently. This system needs to distinguish between natural phenomena and actual attacks, determine appropriate response levels, and deploy countermeasures, all without triggering unnecessary escalation with potential intelligent entities. The ethical programming for such systems presents challenges almost as significant as the technical requirements. Offensive capabilities present their own engineering and ethical challenges. While the primary purpose of weapon systems would be defensive, they must be sufficiently powerful to serve as effective deterrents. However, weapons powerful enough to protect a starship could also cause devastation on planetary scales if misused. Additionally, weapons fire must not compromise the delicate warp field geometry or drain critical power from essential systems during use. This requires careful integration between offensive systems and the ship's power management network. Stealth considerations add another layer of complexity to defense design. A civilization capable of interstellar travel would likely want to control when and how they are detected by other potential intelligences. However, the physics of starship operation makes true stealth virtually impossible. The enormous energy emissions from the propulsion and life support systems would be detectable across vast distances with sufficiently advanced sensors. Instead, defensive systems would focus on maintaining quantum silence, minimizing detectable quantum signatures that could reveal detailed information about the vessel's capabilities and intentions rather than attempting complete invisibility. Point defense systems represent the final line of protection against physical threats that penetrate the outer defensive layers. These would likely combine hypervelocity projectile weapons, directed energy systems, and kinetic interceptors capable of neutralizing threats seconds before impact. The targeting systems for these defenses must track and predict the paths of objects moving at significant fractions of light speed, requiring computation capabilities thousands of times more powerful than current military systems. Radiation protection incorporates both defensive shielding and active countermeasures. Natural sources like cosmic rays represent a constant background threat, but more acute radiation dangers come from solar flares, nearby supernovae, or potential weapons. The shield system must adapt dynamically to different radiation types and intensities, actively absorbing or deflecting harmful particles while maintaining normal operation. For extreme radiation events, the ship might generate temporary enhanced shields at the cost of significant power redirection from other systems. Internal security systems extend the defensive perimeter inside the vessel itself, on a ship designed to operate for generations. The possibility of internal conflict or sabotage cannot be ignored. Non-lethal security measures including selective gravity control, advanced biometric identification, and compartmentalization of critical systems would allow the crew to contain internal threats without causing permanent harm to valuable crew members. These systems require careful design to prevent misuse while remaining effective during genuine emergencies. The psychological impact of defensive systems on crew morale represents a subtle but important consideration. Living aboard a vessel surrounded by layers of protective systems constantly monitoring for threats could create an atmosphere of perpetual siege mentality. Careful interface design would present defense status information in ways that reassure rather than alarm the crew during normal operations, while still enabling rapid response during genuine emergencies. Testing these integrated defensive systems presents unique challenges, as many potential threats cannot be realistically simulated prior to actual mission conditions. Virtual testing using quantum simulations would allow engineers to model scenarios too dangerous for physical testing. But the inherent uncertainty of encountering truly unknown phenomena means that defensive systems must incorporate significant adaptive capabilities. The Defense AI would continuously learn and evolve its response patterns throughout the mission, effectively becoming more sophisticated with each encounter. The interconnection between defensive systems and other ship functions creates cascading complexity that defies complete modeling. A successful defense strategy requires not just technological sophistication, but a holistic understanding of how defensive measures integrate with propulsion, life support, navigation, and social systems. This systems-level integration represents perhaps the greatest engineering challenge in creating a truly viable interstellar vessel capable of protecting its irreplaceable cargo of human lives and civilization knowledge across the vast and potentially hostile ocean of interstellar space. The protective capabilities of any starship are only as effective as the materials from which it's constructed, while defense systems actively respond to threats. The structural materials of the ship must passively withstand the harsh realities of interstellar space for decades or even centuries without failure. Construction and materials engineering for the eternal vacuum represent challenges distinct from anything faced in terrestrial or even conventional space engineering. The fundamental problem is material degradation over extreme timescales. Materials that perform admirably for years or even decades in space can become dangerously compromised over century-long missions. Cosmic radiation gradually breaks down molecular bonds in everything from metals to plastics to ceramics, leading to embrittlement, stress fractures, and eventual structural failure. Engineers must develop materials where this degradation occurs so slowly that even after 100 years, components retain sufficient structural integrity to perform their functions safely. Radiation-resistant materials currently under development incorporate complex molecular structures that can absorb radiation damage without compromising their essential properties. These include self-healing polymers with molecular bonds that reconnect after being broken by radiation, and ceramic metal composites that trap radiation damage in specifically designed sacrifice zones within the material structure. The most advanced designs incorporate nanoscale repair mechanisms, essentially tiny machines built into the material itself that continuously restore damaged molecular structures using ambient energy. Thermal expansion presents another significant challenge for large-scale structures in space. The side of the ship facing a star might reach temperatures of hundreds of degrees, while the shadow side simultaneously experiences temperatures approaching absolute zero. This temperature differential creates enormous stresses that would tear conventional materials apart over time. Engineers must incorporate expansion joints throughout the ship's 6-kilometre hull that can flex and adjust continuously while maintaining perfect seals against the vacuum of space. These joints themselves must function flawlessly for a century without maintenance in some locations. The development of space concrete represents one promising approach to large-scale construction. Created using regolith, the loose material covering solid rock from moons or asteroids combined with binding agents and carbon nanotube reinforcement. This material offers compression strength far exceeding terrestrial concrete while weighing significantly less. The production process could utilize resources available in space rather than requiring all building materials to be launched from Earth, dramatically reducing construction costs. Space concrete could form the bulk structural elements of the vessel, with more specialized materials used for critical components. For components requiring exceptional strength-to-weight ratios, fifth-generation metal alloys incorporate elements that don't naturally occur on Earth. These artificial elements, created in particle accelerators, possess unique properties that allow for materials with previously impossible combinations of lightness, strength, and radiation resistance. For example, theoretical elements beyond the current periodic table might enable superconducting materials that operate at normal ship temperatures, or structural components with tensile strength approaching the theoretical maximum allowed by physics. The actual construction process for kilometre-scale vessels presents challenges as significant as the materials themselves. Assembly would require autonomous robotic systems capable of operating continuously for decades, replacing each other when individual units fail. These construction robots would range from large assemblers handling major structural components to microscopic machines that perform molecular-level quality control. The coordination of thousands of robots working simultaneously across vast distances requires distributed artificial intelligence networks that can adapt to unexpected challenges without human intervention. Molecular manufacturing techniques represent the most sophisticated aspect of space construction. For components with critical functions, traditional manufacturing tolerances are inadequate. Materials must be fabricated with atomic precision, as microscopic imperfections can propagate through kilometre-scale structures and eventually lead to catastrophic failures. This level of precision manufacturing requires molecular assemblers, devices that can position individual atoms with perfect accuracy to build components from the bottom up, rather than carving them from larger pieces of material. The joints connecting different sections of the vessel present particular challenges. These must maintain structural integrity while accommodating thermal expansion, vibration, and the stress of occasional high-G maneuvers. Current experimental designs use biomimetic approaches, creating joint structures inspired by human tendons and ligaments but using synthetic materials that can withstand vacuum and radiation. These flexible connections would incorporate multiple redundant elements so that individual failures don't compromise overall structural integrity. Micrometeoroid protection requires special consideration for long-duration missions. Even tiny particles travelling at relative velocities of tens of kilometres per second carry enough kinetic energy to penetrate conventional hull materials. Multiple layer protection systems, known as Whipple shields, disperse the energy of impacts across sacrificial outer layers before they can reach critical inner structures. For century-long missions, these shields must be either self-repairing or easily replaceable by maintenance systems, as the accumulation of even minor damage over decades could compromise their effectiveness. Transparency presents a surprising materials challenge. Windows and observation ports provide psychological benefits to the crew, but introduce structural weaknesses. Traditional silica-based glass degrades under constant radiation exposure, becoming cloudy and brittle. Transparent aluminum oxynitride and similar ceramics offer better radiation resistance, but still face long-term degradation issues. The most promising solutions involve dynamic, transparent materials that continuously reorganize their molecular structure to repair radiation damage, maintaining clarity indefinitely without developing the microscopic cracks that lead to catastrophic failures. The adhesives and sealants binding different materials together must maintain their properties for centuries without the hardening, embrittlement, or outgassing that affects conventional products in space. Some proposed solutions involve living materials, engineered organisms that continuously produce binding compounds, essentially creating biological welds that heal and strengthen over time rather than degrading. These biological components would need to be engineered to survive in vacuum conditions or be contained within specialized habitats integrated into the ship's structure. The ship's outer hull must incorporate sophisticated sensors throughout its structure to monitor for damage and material fatigue. This structural nervous system would consist of billions of networked sensors embedded directly into construction materials, providing continuous real-time data on the condition of every critical component. Early detection of potential failures allows for preventative maintenance before catastrophic problems develop. The most advanced designs incorporate this sensor network directly into the atomic structure of materials, making the entire ship effectively self-aware of its physical condition. The integration of all these material and construction technologies creates a vessel that's less a static object and more a dynamic, self-maintaining organism. While the engineering challenges are immense, they represent a natural progression of materials science and construction techniques already under development. The resulting structures would be the most durable objects ever created by humanity, designed to preserve human life and civilization across gulfs of space and time that currently seem insurmountable, managing a starship with millions of interconnected systems, each critical for the survival of thousands of people, requires computational capabilities far beyond anything currently existing. Quantum computing for ship management represents the nervous system of any interstellar vessel, processing billions of variables simultaneously to maintain the delicate balance needed for long-term survival in space. Conventional computing architectures fundamentally cannot handle the computational demands of interstellar travel. Modern supercomputers use parallel processing to break problems into smaller parts that can be solved simultaneously. But many calculations required for Starship operations cannot be effectively parallelized. Quantum computers operate on entirely different principles, using quantum bits or qubits that exist in multiple states simultaneously thanks to the principle of superposition. This allows quantum systems to evaluate multiple solutions to complex problems in a single operation rather than sequentially testing possibilities. Stable phase quantum computing represents the most promising approach for ship management systems. These computers maintain quantum coherence, the delicate state where qubits maintain superposition through sophisticated error correction and isolation from environmental interference. Aboard a starship, these systems would perform real-time calculations for warp field geometry, life support optimization, DOT, and defensive response planning that would take centuries on classical computers. The computational core would likely consist of multiple quantum processors operating at near absolute zero temperatures, shielded from both radiation and electromagnetic interference by nested superconducting chambers. Artificial intelligence distributes computational resources dynamically across millions of subsystems, prioritizing based on constantly shifting needs. Rather than a single central computer, the ship would employ a hierarchical network of specialized quantum processors dedicated to specific functions but capable of reassigning resources during emergencies. This distributed architecture prevents single-point failures from compromising the entire computational infrastructure while allowing for efficient resource allocation during normal operations. The management, I would constantly evaluate system performance, shifting computational resources to address emerging challenges before they become critical. The security implications of having essentially the entire crew's lives dependent on computational systems necessitate extraordinary precautions. Quintuple neural backups store complete copies of critical code in different physical formats and locations throughout the ship, ensuring that no single catastrophic event could corrupt all versions simultaneously. These backups utilize fundamentally different storage technologies, from traditional quantum memory to biological data storage in engineered DNA to atomic-level engravings on ultra-stable crystal matrices. This diversity of storage mechanisms protects against both conventional data corruption and novel threats that might affect particular storage technologies. Cybersecurity aboard an interstellar vessel faces the unique challenge of protecting against attack methods that don't yet exist at launch. During a 100-year mission, computing technology throughout the galaxy would continue evolving, potentially developing hacking techniques unimaginable to the original security designers. To address this, ship systems would incorporate adaptive security algorithms capable of identifying and responding to novel threat patterns. Quantum encryption provides mathematical security guarantees against certain types of attacks, while air-gapped systems physically isolate the most critical functions from any external access. The complexity of ship-wide systems exceeds human cognitive capabilities, requiring brain-computer interfaces that allow operators to directly perceive multidimensional data. These neural interfaces translate the ship's status into intuitive sensory experiences, allowing human operators to feel imbalances in the warp field or see patterns in life support fluctuations that would be incomprehensible as raw data. This human-machine symbiosis combines the pattern recognition and intuitive understanding of human minds with the raw processing power of quantum systems, creating oversight capabilities that neither could achieve alone. Predictive maintenance represents one of the most critical applications of shipboard quantum computing. By creating detailed quantum simulations of every significant component, the system can predict failures before they occur based on subtle precursor signals invisible to conventional monitoring. These simulations incorporate the accumulated operational history of components along with theoretical models of degradation mechanisms, allowing maintenance to be performed precisely when needed rather than on arbitrary schedules. This optimization ensures critical systems remain operational throughout the mission while minimizing unnecessary maintenance that wastes limited resources. Managing data storage for a century-long mission presents unique challenges. The ship must maintain perfect records of everything from engineering specifications to medical histories to cultural archives, with zero tolerance for data loss over decades. Beyond multiple physical backups, information would be encoded in overlapping error-correcting formats that allow complete reconstruction even if significant portions become corrupted. Some particularly critical data might be stored in redundant atomic patterns within specially designed crystal matrices that remain stable for millennia, effectively creating information engraved at the molecular level that could survive even catastrophic ship damage. The interaction between human operators and artificial intelligence creates complex operational dynamics. The ship's AI systems would possess capabilities far beyond human comprehension in specific domains while lacking the general adaptability and intuition of human minds. This creates a symbiotic relationship where machine intelligence handles routine operations and complex calculations while human operators provide oversight, creativity, and ethical judgment. The interface between these two types of intelligence requires careful design to prevent misunderstandings while maximizing the strengths of each. Power allocation for computational systems introduces additional complexity. Quantum processors require significant energy for both operation and cooling, yet must function continuously without interruption. The power management system must balance computational needs against other critical ship functions, potentially reducing processing capacity for non-essential functions during energy constraints. Superconducting power delivery systems minimize transmission losses, while quantum error correction algorithms adapt to reduced resources by prioritizing accuracy in critical calculations over computational speed. The ethical programming of ship management systems represents perhaps the most philosophically challenging aspect of their development. These systems must make life or death decisions when situations arise too quickly for human intervention, requiring sophisticated ethical frameworks that align with human values while being explicitly encoded in mathematical terms. Different cultural perspectives on ethics must be reconciled into operational parameters that the entire crew can trust with their lives. This machine ethics development process would likely take decades before a ship could be launched, with extensive testing in simulated crisis scenarios. The totality of these quantum computational systems effectively creates a synthetic intelligence distributed throughout the vessel that monitors, maintains, and protects the physical structure and human inhabitants, while not sentient in the human sense. This integrated computational network would possess capabilities far beyond current AI systems, approaching a form of specialized machine consciousness focused entirely on mission success and crew survival. The development of these systems represents not just an engineering challenge, but a new frontier in the relationship between human and machine intelligence, a partnership where each compensates for the limitations of the other during humanity's greatest journey among the stars. While computational systems manage the vessel's operations, physical movement within solar systems requires conventional propulsion entirely different from the warp drive used for interstellar travel. Space warp technology, with its enormous energy requirements and complex space-time manipulations, proves impractical and potentially dangerous for precise maneuvers near planetary bodies or other spacecraft. Conventional propulsion systems for local maneuvers represent a critical component of any interstellar vessel's design, enabling everything from course corrections to docking operations. The fundamental challenge lies in the transition between propulsion modes. A ship traveling through interstellar space using a warp bubble must safely deactivate this system when approaching destination star systems, then rely on conventional engines for final approach and positioning. This transition represents one of the most dangerous phases of interstellar travel, comparable to atmospheric re-entry for early spacecraft, but with significantly higher energies involved. The conventional drive systems must activate precisely as the warp field collapses, providing immediate control to prevent the ship from drifting unpredictably in the destination system. Helium-3 fusion drives represent the most promising technology for primary conventional propulsion. These engines achieve specific impulse ratings of approximately 1.2 million seconds, roughly 200 times more efficient than the best chemical rockets currently in use. This efficiency allows for sustained acceleration of 0.1 g for years without significant refueling, enabling controlled deceleration into star systems and precise orbital insertions around destination planets. The fuel requirements remain manageable because helium-3 can be harvested from gas giant atmospheres in the destination system, allowing for refueling before return journeys. The plasma exhaust from conventional engines introduces unique challenges for ships that also employ warp technology. The high-energy particles ejected from fusion drives can interfere with the delicate geometry of space-time around a warp field, potentially destabilizing the bubble if both systems operate in close temporal proximity. Engineers must develop sophisticated magnetic containment systems that prevent exhaust particles from interacting with residual warp field components during transition phases. These containment systems direct the plasma exhaust along safe vectors that minimize interference with sensors and other ship systems while maximizing propulsive efficiency. Inertial fields become critically important during conventional maneuvers that may subject the ship to significant accelerations. While sustained low acceleration is preferred for efficiency reasons, emergency situations might require rapid course changes generating forces of dozens of Gs, enough to destroy both the structural integrity of the ship and the bodies of any unprotected crew members. Advanced inertial dampening fields selectively counteract these acceleration forces throughout the vessel, protecting both the structure and inhabitants during high-stress maneuvers. These systems require enormous power during operation but prove essential for survival during evasive actions or collision avoidance. The redundancy requirements for conventional propulsion far exceed those of most other ship systems. While warp drive failure in deep space creates significant problems, the ship remains intact and can potentially repair the system. Conventional drive failure during planetary approach or collision avoidance maneuvers could result in immediate catastrophe with no recovery opportunity. This necessitates quintuple redundancy, 5 completely independent propulsion systems, each capable of providing sufficient thrust for emergency operations. These backup systems utilize different technologies and power sources to eliminate common failure modes, ensuring propulsion capability even after multiple system failures. Precise thrust synchronization presents another significant challenge. For a vessel potentially measuring 6 kilometers in length, engines positioned at different points along the hull must fire with perfect coordination to prevent creating torque that could tear the ship apart. The timing systems must account for relativistic delays in communication between widely separated ship sections, as even light-speed signals take microseconds to travel the length of the vessel. Quantum-entangled communication links provide instantaneous coordination between engine controllers, ensuring that thrust vectors remain perfectly aligned regardless of separation distance or relative velocity. Reaction control systems handle the fine adjustments necessary for docking maneuvers and attitude control. These smaller thrusters use a variety of technologies from cold gas systems for the most delicate adjustments to miniaturized fusion thrusters for larger orientation changes, distributed throughout the vessel in optimized patterns. These thrusters provide 6 degrees of freedom control with redundant coverage, ensuring that attitude control remains possible even if multiple thrusters fail. The reaction control computer continuously calculates optimal firing patterns that minimize fuel usage while achieving precise positioning, handling the complex physics of rotating and translating an asymmetric body with variable mass distribution. Fuel management introduces its own complexities for long-duration missions, while antimatter serves as the primary energy source for warp propulsion. Conventional engines typically use fusion fuels like deuterium, tritium, and helium-3. These fuels must be stored in specialized containment systems that prevent degradation over decades while remaining immediately accessible when needed. Some designs incorporate fuel generation capabilities that can produce tritium through neutron bombardment of lithium or extract deuterium from collected interstellar hydrogen, reducing dependence on the finite fuel supplies carried from Earth. Navigation sensors dedicated to conventional propulsion operate independently from the main navigational array, providing redundancy for critical maneuvering data. These include LiDAR systems for precise distance measurements, gravitational mapping arrays that detect the subtle variations in gravitational fields around planetary bodies, and optical cameras with computer vision processing that can identify visual landmarks for position confirmation. This sensor fusion approach ensures accurate navigational data even if primary systems are compromised by damage or interference. The integration between conventional propulsion and other ship systems creates cascading design challenges. Engine radiation and electromagnetic emissions must be shielded to prevent interference with sensitive scientific equipment and habitat areas. The structural attachment points for massive engine assemblies must distribute thrust loads throughout the ship's framework without creating stress concentrations that could lead to structural failure. Power systems must provide both steady operational energy and handle the massive surge requirements during emergency maneuvers, requiring sophisticated load balancing and prioritization algorithms, while the engineering challenges of conventional propulsion for interstellar vessels are substantial. They build upon technologies and principles already well established in current spacecraft design. The primary innovations lie in scale, integration, and reliability, rather than requiring fundamentally new physical principles. This makes conventional propulsion systems one of the more straightforward aspects of interstellar vessel design, though still requiring significant advances beyond current capabilities to achieve the necessary performance and reliability for century-long missions between the stars. Beyond the technical systems that enable interstellar travel, the human element introduces unique challenges that may ultimately prove more difficult to solve than any engineering problem. The psychology of multi-generational crews represents a frontier of knowledge with few historical parallels. Understanding how humans adapt to confined environments across lifespans and generations requires insights from disciplines ranging from clinical psychology to cultural anthropology to evolutionary biology. The most fundamental psychological challenge stems from the simple fact that while the first generation of crew members voluntarily chose their mission, subsequent generations are born into a situation they never selected. Children born aboard an interstellar vessel have no experience of planetary life, no concept of open skies or natural ecosystems beyond simulations and educational materials. Their entire universe consists of the ship's interior spaces, creating a psychological framework profoundly different from Earth-evolved human minds. Psychologists have termed this the horizon lost syndrome, a condition where individuals never develop the neural pathways associated with processing vast open spaces and natural environments. This syndrome manifests in various ways, from subtle differences in spatial processing to more profound impacts on creativity and abstract thinking. Research in confined Earth environments like underground facilities suggests that children raised without exposure to natural horizons develop different depth perception and may struggle with certain types of spatial reasoning. Conversely, they often excel at navigating complex enclosed environments and demonstrate enhanced awareness of subtle environmental changes within their habitat. These adaptations happen at a neurological level during development, creating minds optimized for the spaceship environment rather than planetary conditions. The social psychology of confined communities introduces additional complexities. Earth-based isolation studies in environments like Antarctic research stations and submarine deployments provide limited insights, but these typically involve small groups for periods measured in months, rather than thousands of people for centuries. The closest historical analogues might be isolated island communities or remote cultural groups, which often developed distinctive social structures and psychological adaptations over generations. Studies of these populations suggest that successful isolated communities develop strong cultural institutions that regulate social interactions and provide psychological stability through shared meaning systems. The contract between generations becomes a central psychological and philosophical issue for multi-generational missions. The first generation makes decisions that will irrevocably shape the lives of their descendants for centuries, from resource allocation to cultural practices to mission objectives. This creates potential for intergenerational conflict as later generations may question decisions made by ancestors they never knew, particularly if those decisions result in hardship or limitations. Psychological research suggests that transparent decision-making processes and cultural narratives that honor ancestral sacrifices while acknowledging the agency of current generations can help mitigate these tensions. Family structures aboard interstellar vessels would likely evolve beyond Earth norms in response to the unique environment. The isolated population with limited genetic diversity creates both biological and social pressures for non-traditional family arrangements. Extended family networks that distribute childcare responsibilities among multiple adults offer advantages in educational continuity and social stability. Some theoretical models propose sectional families where children form significant bonds with adult mentors throughout different ship departments, creating knowledge transfer pathways while establishing backup caregiving relationships if biological parents become unavailable through accident or illness. The psychological impact of death takes on different dimensions in a closed system where resources are precious and population balance is critical. Earth cultures developed diverse mourning rituals and beliefs about death that provide psychological comfort and social continuity. Aboard a generation ship, death represents not just personal loss, but also the recycling of limited biological resources back into the closed ecosystem. This necessitates funeral practices that honor the psychological need for grief while acknowledging the practical necessity of complete material recycling. Psychologists suggest that rituals emphasizing contribution and continuation, how the deceased continues to support the community through the recycling of their physical form, may help reconcile these seemingly contradictory aspects. Privacy versus surveillance creates ongoing psychological tension in confined environments where individual actions can impact collective survival. Earth-based studies of isolated communities show that lack of privacy contributes significantly to stress and interpersonal conflict. Yet safety concerns in a spacecraft environment necessitate monitoring of potentially dangerous areas and activities. Successful psychological design requires creating genuine private spaces where surveillance is absent or strictly limited, while maintaining necessary monitoring of critical systems and high-risk environments. The perceived fairness of these boundaries, that privacy restrictions apply equally to all regardless of status, proves crucial for psychological acceptance. The phenomenon of presentism cultural represents a particular concern for later generations. This psychological tendency causes people born on the ship to consider their current environment as the natural state of humanity rather than an extraordinary technological achievement with a specific purpose. Educational programs must continuously contextualize the ship environment within the larger human story to maintain mission focus across generations. Some proposed approaches include immersive virtual reality experiences of Earth environments, cultural ceremonies marking the mission's progress, and educational curricula that emphasize both Earth history and destination expectations. The development of ship-specific cultural identity offers both challenges and opportunities for psychological health. A distinct ship culture with its own traditions, expressions, and values naturally emerges in any isolated community, potentially diverging significantly from the originating Earth culture over generations. This cultural evolution can provide psychological resilience through shared identity and meaning, but may eventually create communication barriers with Earth or other human settlements. Some theoretical models suggest actively managing cultural evolution through educational systems and cultural institutions to maintain core human values while allowing adaptive development of traditions appropriate to the ship environment. Addressing the fundamental human need for novelty and exploration, what some psychologists call horizon hunger, represents perhaps the most subtle but crucial psychological challenge for multi-generational missions. Humans evolved with drives toward exploration and new experiences that cannot be satisfied in the traditional sense within a confined vessel. Virtual reality environments offer partial solutions by providing novel sensory experiences without physical travel, scheduled reorganizations of living spaces, rotating job assignments, and deliberately introduced environmental variations can create the perception of novelty within physical constraints. Educational systems might emphasize exploration through scientific discovery and creative expression rather than physical movement, channeling the exploratory drive into activities compatible with ship limitations. The success of any multi-generational mission ultimately depends as much on psychological sustainability as technological reliability, while engineering systems can be designed with redundancies and fail-safes. Human psychology requires environments that satisfy fundamental needs for meaning, connection, privacy, and stimulation. Creating these conditions within the constraints of an interstellar vessel represents a design challenge no less daunting than developing the propulsion systems that power the physical journey between stars. The psychological challenges of long-duration space missions directly influence the development of medical systems for multi-generational space travel. Beyond maintaining mental health, interstellar vessels must address the full spectrum of human medical needs across multiple lifetimes without external support. Medical technology for intergenerational voyages represents one of the most comprehensive healthcare systems ever designed, combining preventive care, emergency response, and evolutionary adaptation within a closed environment. Complete genetic banks form the foundation of long-term medical planning aboard interstellar vessels. These repositories preserve the genetic diversity of the founding population, storing samples from every crew member in multiple formats and locations throughout the ship. This genetic library serves multiple critical functions beyond simple preservation. It provides backup genetic material for potential reproductive assistance, allows for screening of dangerous recessive traits that might emerge in later generations, and enables correction of radiation-induced mutations that inevitably accumulate during long-term space exposure. The most sophisticated systems maintain not just DNA samples, but complete stem cell lines from each crew member, allowing for potential regeneration of tissues or organs identical to the original donor. Automated diagnostic systems become essential for identifying and addressing medical conditions that might emerge during the voyage. These systems combine advanced imaging technologies, molecular scanners capable of detecting pathogens at extremely low concentrations, and artificial intelligence that continuously updates its knowledge base as new medical information becomes available. Unlike Earth-based medical AI that can be regularly updated from global research networks, ship systems must independently identify novel disease patterns that emerge in the closed environment. This requires sophisticated pattern recognition algorithms that can distinguish between normal biological variations and potentially dangerous new conditions without external confirmation. Preventive medicine takes on unprecedented importance in closed-system vessels where epidemics could rapidly spread through the entire population with no possibility of external assistance. Regular health monitoring becomes a standard part of ship life, with continuous environmental sampling for pathogens, regular biometric tracking of all crew members, and automated systems that can identify concerning health trends before individuals even become symptomatic. Vaccination protocols must be maintained across generations, requiring careful preservation of immunological knowledge and materials. The ship's medical database would include complete pathogen profiles with regularly updated treatment protocols adapted to any mutations observed in the closed environment. Hibernation technologies, while not intended for routine use, would be maintained as emergency options throughout the journey. These systems could preserve crew members during extreme resource shortages or serve as last resort options for patients with conditions beyond current treatment capabilities. Modern experimental cryogenic approaches requiring complex chemical perfusion would likely be replaced by metabolic suspension techniques that induce hyper-efficient states similar to extreme hibernation in certain mammals. These technologies present complex ethical considerations regarding decision-making authority for placing individuals in suspended animation and protocols for revival timing. Surgical interventions in deep space require completely automated systems capable of performing complex procedures with minimal human supervision. Robotic surgical platforms would combine high-precision mechanical manipulation with advanced imaging systems that can visualize tissues at the cellular level in real time. These systems would be designed to operate autonomously if necessary, ensuring that critical procedures could continue even if all medically trained personnel were incapacitated. The surgical robots would maintain continuously updated knowledge bases incorporating both Earth medical history and accumulated experience from procedures performed during the mission. Pharmaceutical manufacturing capabilities must be completely self-contained, able to synthesize any required medication from basic chemical precursors available on the ship. This requires not just production facilities, but comprehensive databases of chemical synthesis pathways and biological testing protocols to ensure safety and efficacy. Biological production systems using engineered microorganisms to create complex organic molecules would likely supplement traditional chemical synthesis methods. The most advanced designs include adaptive pharmaceutical development, systems capable of designing and producing novel medications in response to emerging conditions not anticipated before launch. Radiation medicine becomes a specialized field critical to long-term crew health. Cosmic radiation exposure accumulates over decades in space, potentially causing increased cancer rates, fertility issues, and cellular damage that accelerates aging. Medical countermeasures would include regular administration of radioprotective compounds that help repair cellular damage, specialized screening protocols for radiation-related disorders, and treatments designed to address the unique manifestations of conditions caused by cosmic radiation exposure. Medical staff would track lifetime radiation exposure for every crew member, adjusting work assignments and living areas to equitably distribute unavoidable exposure among the population. Adaptive genetic modifications represent perhaps the most controversial aspect of intergenerational medical technology. While the first generation of crew would be essentially unmodified Earth humans, subsequent generations might benefit from carefully selected genetic adaptations to the space environment. These could include enhanced radiation resistance, improved calcium retention to prevent bone density loss, or optimized cardiovascular function for the ship's specific gravity conditions. Such modifications would be implemented only with rigorous ethical oversight and extensive testing, targeting specific adaptations rather than general enhancement while maintaining fundamental human characteristics. Reproductive medicine takes on special significance in a closed population concerned with both genetic health and demographic stability. Advanced fertility technologies would be maintained to help manage genetic diversity across generations, while contraception would be readily available to support population stability. Genetic counseling would become routine for potential parents, providing information about possible heritable conditions and optimal timing for conception based on population needs. These reproductive services require balancing individual reproductive autonomy against the collective needs of the ship's limited resource environment. Mental health services would be fully integrated with physical medicine, recognizing the profound connections between psychological well-being and physical health. Therapeutic approaches would combine traditional psychological techniques with neurochemical interventions and virtual reality environments designed for specific treatment purposes. The ship's medical AI would monitor subtle behavioral changes that might indicate developing psychological issues, allowing for early intervention before conditions become severe. These mental health systems would adapt specifically to address the unique stresses of multi-generational space travel, including the horizon lost syndrome and intergenerational identity conflicts previously discussed. The medical facilities themselves would be distributed throughout the vessel rather than concentrated in a single location, ensuring that emergency care remains accessible even if sections of the ship become temporarily isolated due to accidents or systems failures. Each residential sector would maintain at least basic treatment capabilities, while more specialized facilities handle complex cases and research. This distributed approach creates redundancy while reducing response time during emergencies, critical when dealing with conditions where minutes can determine survival outcomes. The medical technologies aboard interstellar vessels ultimately represent not just tools for maintaining health, but systems for managing human biological adaptation to completely new living conditions over generational timescales. While addressing immediate health needs, they simultaneously lay groundwork for the long-term flourishing of human biology in environments radically different from those in which we evolved on Earth. While medical systems maintain human health, the ship's agricultural systems provide the sustenance necessary for survival. Space agriculture and self-sustaining food production represent one of the most visible and vital aspects of daily life aboard an interstellar vessel. Unlike the International Space Station, where food arrives regularly on supply missions, interstellar vessels must produce every calorie consumed by the crew for centuries without external inputs. This requires agricultural systems of unprecedented efficiency and reliability. Vertical hydroponic systems form the backbone of space-based food production, occupying dedicated sectors throughout the vessel. These multi-layered growing environments maximize production per cubic meter of space, producing up to 10 times more food than traditional soil-based farming with the same footprint. Specialized lighting systems provide precisely tuned wavelengths that optimize photosynthetic efficiency while minimizing energy consumption. Nutrient delivery systems circulate carefully formulated solutions that provide exactly what each plant variety needs during different growth phases. These hydroponic arrays would grow primarily high-calorie staple crops like grains, legumes, and starchy vegetables that form dietary foundations for most human cultures. Plant genetics plays a crucial role in space agriculture efficiency. Earth crops evolved under conditions vastly different from those aboard spacecraft, with different gravitational forces, light spectra, and atmospheric compositions. Genetically engineered varieties optimize oxygen production while maximizing caloric yield per resource input. Some varieties might be modified to produce multiple nutritional components, for example, tomato plants that produce fruit with enhanced protein content or leafy greens with improved essential fatty acid profiles. These modifications focus on nutritional density and growth efficiency rather than characteristics valued in Earth agriculture like drought resistance or pest deterrence. The controlled environment creates opportunities for continuous production impossible on seasonally limited Earth. Growing cycles are staggered to provide constant harvests, with computerized management systems tracking thousands of individual plants at different growth stages. Automated harvesting and replanting systems reduce labor requirements while ensuring optimal timing for maximum yield. This perpetual growth cycle requires precise environmental control systems maintaining ideal temperature, humidity, and air circulation throughout growing areas. The most advanced designs incorporate adaptive monitoring that adjusts growing conditions in real-time response to plant biometrics, optimizing production continuously. Insect farming provides highly efficient protein sources that convert plant waste into nutritionally complete food with minimal resource inputs. Crickets, mealworms, and similar species can produce 9 times more edible protein than cattle from the same food input while requiring fraction of the space and water. These protein sources would likely be processed into forms familiar and palatable to the crew, protein isolates used in various dishes rather than whole insects for most meals. Insect farming systems would be designed for complete automation, with minimal human intervention required for maintenance. These systems create critical links in nutrient cycles, converting inedible plant portions and food waste back into valuable protein. Synthetic bacteria engineered to directly convert carbon dioxide into complex organic molecules represent the most advanced biological production systems. These microorganisms essentially perform artificial photosynthesis with efficiency exceeding natural plants, creating carbohydrates, lipids, and even complete proteins from atmospheric carbon dioxide, water, and energy input. Bioreactors throughout the ship would cultivate these organisms in contained environments, producing nutrient-dense base materials that can be further processed into various food products. This bacterial production serves as a critical backup system that could maintain basic nutrition even if plant systems suffered catastrophic failure. Fungal production forms another critical component of the food system. Mushrooms and mycelium-based foods provide protein, vitamins, and unique flavors while growing on minimal substrates derived from inedible plant materials. Fungal production requires minimal light compared to plants, allowing efficient use of spaces unsuitable for photosynthetic organisms. Certain fungi also produce compounds that mimic animal protein flavors, helping create satisfying meat alternatives that support culinary variety, too. The rapid growth cycles of fungi, some species complete full production in just days, make them valuable for responsive production when food needs suddenly increase. Accelerated growth systems provide emergency food production capabilities when normal production is disrupted or demand temporarily exceeds supply. These systems sacrifice long-term efficiency for rapid output, using intensified lighting, elevated carbon dioxide levels, and optimized nutrient delivery to produce limited harvests of fast-growing crops in half the normal time. While energetically expensive and unsustainable for regular use, these systems provide crucial food security during crises. Separate dedicated facilities for accelerated production would be maintained in standby mode, ready for immediate activation when needed. The integration of food production with atmospheric recycling creates a symbiotic relationship between these critical systems. Plants naturally convert carbon dioxide exhaled by the crew back into oxygen through photosynthesis, while also removing certain airborne contaminants through biofiltration effects. This integration extends to water systems, with plant transpiration playing key roles in humidity management and water purification. The agricultural sectors effectively function as the lungs of the ship, maintaining atmospheric balance while producing food. This dual functionality makes agricultural systems among the most carefully protected aboard the vessel. With multiple redundancies and backup systems, aquaculture systems complement plant agriculture by producing fish and aquatic plants in water-based ecosystems. These controlled aquatic environments produce high-quality protein and essential fatty acids difficult to obtain from plant sources alone. The waste products from fish become valuable nutrients for hydroponically grown plants, creating closed-loop systems that maximize resource efficiency. Species like tilapia and certain algae thrive in relatively small, contained systems while providing significant nutritional benefits. Aquaponic combinations of fish and plant production represent some of the most efficient food production systems possible in limited space environments. Food processing capabilities transform raw agricultural outputs into palatable, nutritionally complete meals that maintain crew morale across generations. While functional nutrition could theoretically be achieved through minimal processing, psychological well-being requires meals that provide sensory pleasure and cultural continuity. Processing facilities would include systems for creating texturized proteins that mimic animal products, flavor extraction and enhancement technologies, and preservation methods that maintain food safety without refrigeration. These processing systems would be designed for flexibility, allowing adaptation to changing agricultural outputs while creating food products aligned with evolving cultural preferences across generations. The combined agricultural systems aboard an interstellar vessel represent humanity's most comprehensive attempt to recreate Earth's natural food production capabilities in a completely artificial environment. Success requires not just biological engineering, but deep integration with the vessel's energy, water, and waste management systems. When functioning properly, these agricultural systems create a perpetual cycle of production and consumption that could theoretically continue indefinitely, sustaining human life across the vast distances between stars. The agricultural systems that feed the crew exist within a social framework governed by specialized legal and political structures. As with every aspect of interstellar travel, governance systems for isolated societies must be carefully designed to function without external support for generations. The legal and governmental frameworks aboard a generation ship differ fundamentally from those on Earth, requiring specialized approaches that balance stability with adaptability in a resource-limited environment. The basic governance challenge stems from the vessel's unique status as simultaneously a vehicle, habitat, and complete society. Unlike Earth nations with separate government branches that evolved over centuries, Starship governance systems must be intentionally designed with clear lines of authority and responsibility. Most theoretical models propose hybrid structures combining elements of democracy for long-term policy decisions with more hierarchical systems for technical operations and emergencies. This dual-track approach recognizes that while crew members should have meaningful input into their social organization, certain technical decisions require specialized expertise and rapid implementation that democratic processes might impede. Constitutional frameworks for Starship societies typically establish foundational principles that remain relatively fixed, while creating adaptive mechanisms for addressing unforeseen challenges. These founding documents would explicitly recognize the unique circumstances of space travel, balancing individual rights against the collective survival requirements of the closed system. Critical elements often include resource access guarantees, decision-making procedures, and explicit limitations on authority to prevent tyrannical governance. Unlike Earth constitutions that frequently reference historical precedents or abstract principles, ship constitutions tend toward concrete operational guidelines with clear implementation protocols. Decision-making procedures aboard generation ships must balance thoughtful deliberation with timely action. Many proposed systems employ tiered response frameworks where routine decisions follow deliberative processes with broad input, while emergencies trigger more streamlined authority structures. Artificial intelligence advisory systems often play key roles in these processes, providing objective analysis of complex situations and modeling potential outcomes of different decisions. These AI systems typically lack independent authority, but serve as decision support tools that ensure leadership has access to comprehensive information before making critical choices. Succession of leadership presents particular challenges for multi-generational missions. Earth governments typically transfer power through elections or hereditary succession, but neither system fully addresses the unique needs of century-long voyages. Most designs incorporate carefully planned transitions with overlapping terms, where new leaders train alongside experienced ones before assuming full authority. Some models propose rotating leadership from different ship sectors or specializations, ensuring diverse perspectives while preventing any single group from dominating governance long-term. These succession systems often include objective qualification requirements combining technical expertise with demonstrated judgment and interpersonal skills. Justice systems in closed environments face unique constraints that make Earth-based models impractical. Traditional incarceration wastes valuable space and removes potentially productive crew members from the workforce. Instead, ship-based justice typically emphasizes rehabilitation and restorative approaches focused on reintegrating offenders while addressing harm caused. Minor infractions might result in additional community service requirements or temporary resource access restrictions, while serious offenses could lead to intensive monitoring and compulsory therapy. Only the most dangerous individuals who pose ongoing threats would face long-term containment, and even then in conditions that allow them to contribute productively under appropriate supervision. The concept of property rights undergoes significant evolution in starship societies where virtually all resources are communally critical. While personal possessions would be recognized, larger resources like living quarters, equipment, and raw materials typically operate under stewardship models rather than absolute ownership. Use rights would be allocated based on need and function, with explicit recognition that all resources ultimately belong to the mission rather than individuals. This approach prevents resource hoarding while maintaining incentives for innovation and care of assigned resources. Digital possessions like creative works or software innovations might follow more traditional ownership models as they don't consume physical resources. Emergency protocols represent a critical aspect of ship governance, establishing clear authority structures during crises when normal decision processes might be too slow. These protocols typically define specific emergency conditions that trigger temporary authority changes, along with explicit limitations and sunset provisions that prevent emergency powers from becoming permanent. Crew members would undergo regular training in these protocols to ensure widespread understanding of how authority shifts during different emergency classifications. The transparent design of these systems helps prevent abuse while providing necessary flexibility during genuinely dangerous situations. Privacy balancing in closed environments presents ongoing governance challenges. The ship's safety requirements necessitate certain monitoring systems, particularly in critical areas, yet human psychological health requires private spaces free from surveillance. Successful governance frameworks establish clear boundaries between monitored and private areas, with strict limitations on data retention and usage from necessary monitoring systems. These privacy protections typically receive constitutional-level protections with independent oversight mechanisms to prevent mission security from becoming justification for unnecessary surveillance. Dispute resolution mechanisms take on heightened importance when individuals cannot physically separate from conflicts. Mandatory mediation systems typically serve as first response approaches to interpersonal disputes, with trained mediators helping parties reach mutually acceptable resolutions before conflicts escalate. For disputes that cannot be resolved through mediation, formalized arbitration provides binding decisions based on established principles and precedents. These systems emphasize maintaining functional relationships and community harmony rather than determining absolute right and wrong in every situation. For specialized disputes involving technical matters, expert panels might provide both factual clarification and resolution guidance. Legislative functions aboard generation ships typically involve representative councils drawn from different vessel sections and specializations. These councils develop operational policies that implement constitutional principles in daily life, adapting rules as conditions change over decades. Unlike Earth legislatures that might meet periodically, ship councils often maintain continuous session with rotating membership, ensuring governance continuity while allowing members to maintain their primary duties. Legislative proposals typically undergo simulation testing using AI models that predict implementation outcomes before formal adoption, reducing unintended consequences of well-intentioned policies. Cultural evolution poses particular challenges for legal systems designed to last centuries. Language, values, and social expectations naturally shift across generations, potentially rendering original legal frameworks increasingly disconnected from lived reality. Addressing this requires periodic formalized review processes where each generation explicitly evaluates and affirms or modifies governance structures. These reviews preserve core principles while allowing adaptation to changing circumstances and values. The most successful models balance respect for founding wisdom with recognition that each generation must meaningfully consent to the systems governing their lives. The governance challenges of interstellar vessels ultimately reflect amplified versions of issues facing all human societies, balancing individual freedom with collective needs, maintaining accountability of authority, and adapting institutions to changing circumstances. The confined nature of spacecraft simply makes these tensions more immediate and the consequences of failure more severe. Successful governance design requires not just institutional structures, but cultivating a shared understanding that the ship's systems exist to serve human flourishing across generations in the unique environment of deep space. The governance systems that organize society aboard the vessel depend fundamentally on material resources circulating through the ship's systems. In an environment where nothing can be truly discarded and no new raw materials can be obtained, waste management and circular economy principles reach their ultimate expression. Generation ships require absolutely closed material cycles where every atom aboard must be continuously reused through sophisticated recycling and remanufacturing systems. The fundamental concept distinguishing Starship resource management from even the most advanced Earth-based systems is the complete elimination of the very idea of waste. In terrestrial economies, materials that become too contaminated, mixed, or degraded eventually reach a point where recycling becomes economically impractical, and disposal occurs. In the closed system of an interstellar vessel, no such option exists. Every atom brought aboard at launch must remain in productive use throughout the entire mission. This reality transforms waste processing from an environmental nicety to an absolute survival requirement. Molecular converters represent the most sophisticated recycling technology aboard, capable of breaking down materials to their constituent elements for reconstruction into needed resources. These systems combine advanced physical separation techniques like plasma decomposition with chemical processes that sort mixed materials into pure elemental streams. Nanoscale manipulators then reassemble these basic building blocks into required compounds and structures. While enormously energy-intensive, these systems ensure that even the most complex waste mixtures can be returned to useful form rather than accumulating as unusable material that would eventually overwhelm the ship's storage capacity. Synthetic biology plays critical roles in material recycling, with engineered microorganisms specializing in decomposing specific compounds. Bacteria designed to break down complex polymers, process electronic waste, or detoxify hazardous compounds operate in controlled bioreactors throughout the ship. These biological systems offer energy efficiency advantages over purely mechanical recycling for many materials, particularly organic compounds. The most sophisticated designs use cascading biological systems where the waste products from one organism become food sources for others, creating complete decomposition pathways for even the most resistant materials. Resource tracking systems monitor every significant quantity of material aboard the vessel, creating a continuously updated inventory of all atoms in the closed ecosystem. Advanced tagging technologies ranging from microscopic RFID equivalents to molecular markers allow systems to track materials through multiple use cycles and transformations. This comprehensive accounting ensures nothing is lost from the productive cycle through oversight or neglect. The tracking extends to monitoring subtle changes in material composition over time, identifying potential accumulation of problematic elements before they reach levels affecting system performance. The recycling of rare elements represents particularly critical functions for long-duration missions, while common elements like carbon, hydrogen, and oxygen cycle relatively easily through biological systems. Rare earth elements and precious metals required for electronics and advanced materials cannot be synthesized and must be meticulously recovered from decommissioned equipment. Specialized extraction systems concentrate these elements from waste streams with near-perfect efficiency, ensuring continued availability for manufacturing critical components throughout the century-long mission. Conservation protocols establish strict standards for resource utilization throughout all ship systems. These protocols prioritize designs that minimize material degradation, extend useful lifespans, and facilitate eventual recycling. Products created aboard would be engineered for multiple use phases, perhaps serving first as structural components, then being reprocessed into less demanding applications as they degrade, and finally being completely recycled when no further use is possible. This planned cascade utilization maximizes the service extracted from materials before they require energy-intensive molecular recycling. The social dimensions of material circularity create unique aspects of shipboard culture. Waste generation becomes one of the most serious social transgressions, with strict consequences for actions that needlessly damage or contaminate resources. Education systems place heavy emphasis on understanding material flows and each individual's responsibility within the closed system. Waste management roles, often stigmatized in Earth cultures, typically hold high status in ship societies, recognized as essential for collective survival. This cultural shift represents a necessary adaptation to environmental realities where resource preservation directly connects to survival prospects. Personal possessions under circular economy conditions operate under fundamentally different principles than in consumption-oriented Earth societies. Crew members maintain usage rights rather than permanent ownership of most physical items, with the understanding that materials will eventually return to common pools for reassignment. Durable goods like furniture or tools might circulate through multiple users during their functional lifespan, undergoing refurbishment between users. This approach maximizes utility extracted from materials while maintaining the psychological benefits of having personal items adapted to individual preferences. Manufacturing systems under perfect circularity principles emphasize modular design and standardization of components. Products would share common interface specifications, fastener types, and material formulations to facilitate both repair and eventual recycling. Additive manufacturing techniques, advanced descendants of today's 3D printing, allow creation of customized items without the material waste associated with subtractive processes. These systems typically operate in distributed networks throughout the vessel, producing items on demand close to usage locations rather than maintaining large inventories that tie up materials in unused products. Water recycling represents one of the most visible and critical circular systems aboard. Human bodies continuously cycle water through biological processes, requiring sophisticated purification systems that process everything from humidity in exhaled breath to wastewater from hygiene and sanitation systems. Multiple redundant filtration technologies operating in sequence ensure water purity regardless of input quality, while sophisticated monitoring systems verify safety at molecular levels before reuse. The psychological aspects of water recycling require careful attention, as humans evolved instinctive aversions to water perceived as previously used. Design elements that emphasize the complete molecular transformation between use cycles help overcome these natural but counterproductive responses. Atmospheric cycling complements water systems, with carefully balanced processes that maintain breathable air by removing carbon dioxide, volatile organic compounds, and particulates while replenishing oxygen, beyond basic air quality. These systems must manage trace gas compositions that affect everything from plant growth to human cognitive function. The integration with agricultural systems creates natural air purification cycles, but mechanical systems provide critical backup and fine control capabilities. Unlike water, which remains visible throughout its use cycle, air quality management operates largely invisibly but requires equally sophisticated monitoring and maintenance. Energy considerations profoundly influence all circular economy operations aboard the ship, while atoms remain conserved within the closed system regardless of process efficiency. The energy required to transform materials from less useful to more useful states represents a significant cost against the vessel's limited energy budget. This reality drives continuous refinement of recycling processes to minimize energy consumption while maximizing material recovery. The balance between energy expenditure and material accessibility creates complex optimization challenges that ship systems continuously adjust based on current priorities and resource states. The absolute circularity required for interstellar travel ultimately represents the logical endpoint of sustainable resource management principles already emerging in advanced Earth economies. The fundamental difference lies not in the underlying concepts, but in the unforgiving nature of deep space, which removes any margin for error or waste streams that cannot be recaptured. The engineering and social systems required to maintain perfect material circularity for a century represent some of the most sophisticated aspects of Starship design, transforming an entire vessel into a living example of the closed-loop systems that Earth's biosphere has maintained naturally for billions of years. The perfect circularity of materials within the vessel maintains physical resources, but an interstellar mission exists within a broader context of human civilization. Communication between the vessel and Earth, or other human settlements, represents a unique challenge that shapes both technological systems and social expectations. Interstellar communication systems must overcome fundamental physical limitations while maintaining meaningful connections across gulfs of space and time that stretch human relationships to their limit. The primary challenge for any communication beyond our solar system stems from the immutable speed of light. Radio signals travelling at approximately 300,000 kilometers per second still require years to reach even the nearest star systems. This creates communication delays measured in years or decades, depending on the vessel's distance from Earth. A simple question sent from the ship might not receive a response for 20 years or more, making conventional conversation impossible. This reality fundamentally transforms the nature of communication from interactive dialogue to something more akin to sending time capsules across space. Quantum communication techniques offer partial solutions to these challenges. While quantum entanglement cannot transmit information faster than light, preventing any form of instantaneous communication, it provides unprecedented security and data integrity across vast distances. Quantum encrypted signals remain perfectly secure regardless of transmission distance, protecting sensitive information from interception or corruption. The entanglement properties also provide built-in verification that messages arrive exactly as sent, without the degradation that affects conventional radio transmissions over interstellar distances. Maintaining quantum coherence across light years requires sophisticated error correction systems and redundant entangled particle pairs prepared before the vessel's departure. Data compression becomes critically important when each transmission might represent years of accumulated information. Specialized artificial intelligence systems continuously analyze accumulated data, identifying what information holds greatest value for recipients and compressing decades of ship operations, scientific discoveries, and social developments into transmission packages that maximize informational density. These systems employ context-aware compression that considers what recipients likely already know versus what would be novel or necessary information. A transmission might compress routine operations into brief statistical summaries while preserving complete details of unexpected discoveries or significant events. The linguistic drift phenomenon presents unique challenges for long-duration missions. Natural languages evolve continuously as societies develop new concepts, technologies, and social structures. Over generations, the language spoken aboard the vessel would naturally diverge from Earth languages, developing new vocabulary, grammatical structures, and idiomatic expressions reflecting the unique environment and experiences of the crew. Without intervention, this linguistic evolution could eventually render communication unintelligible despite using the same original language. To address this, communication systems incorporate sophisticated translation layers that track linguistic changes and provide appropriate conversions between ship dialect and Earth standard languages. Backup communication systems distributed throughout the vessel provide critical redundancy for this vital function. Primary communication arrays with high-powered transmitters and sensitive receivers would typically be located on the exterior hull, making them vulnerable to damage from micrometeoroid impacts or other space hazards. Secondary and tertiary systems with independent power supplies ensure that communication capability remains even if significant portions of the vessel become damaged. These distributed systems might offer reduced bandwidth or range compared to primary arrays, but maintain essential connectivity under almost any survivable emergency scenario. Security protocols governing interstellar transmissions balance the need for communication against potential risks of revealing the vessel's position to unknown entities. while the enormous energy emissions from the ship's propulsion and life support systems would be detectable at significant distances by sufficiently advanced civilizations. Directional communications provide more precise positional information. Many theoretical mission protocols include specific guidelines about when omnidirectional versus tightly beamed transmissions should be employed, with higher security settings during passage through unknown regions. Some designs incorporate communication relays left along the vessel's path that can retransmit messages through different vectors, obscuring the ship's current location while maintaining information flow. The content prioritization of transmissions reflects both practical limitations and psychological needs. Technical data, scientific observations, and mission-critical updates typically receive highest bandwidth allocation. However, psychological research indicates that personal messages between separated family members and broader cultural exchanges provide essential emotional support for both ship crew and Earth contacts. Communication systems therefore reserve significant capacity for these seemingly non-essential transmissions, recognizing that maintaining human connections across interstellar distances serves mission success as meaningfully as technical information exchange. The growing time delays as vessels move farther from Earth create psychological adaptation challenges for both senders and recipients. Early in the mission, crews might struggle with the frustration of increasingly delayed responses. As delays extend to decades, communication necessarily transforms from conversation to historical documentation. Messages sent from Earth might address children not yet born when the transmission departed, while responses from the ship might reach Earth generations after the original senders have died. Communication training helps crew members compose messages that remain meaningful across these timescales, focusing on content with lasting significance rather than ephemeral concerns that will be irrelevant by the time a response arrives. The technological challenges of maintaining communication equipment for centuries exceed those of most other ship systems. Transmitter components degrade through normal use, while sensitive receivers require regular recalibration to maintain optimal performance. Communication systems therefore incorporate continuous self-diagnostic capabilities and modular designs allowing component replacement without interrupting basic functionality. The most sophisticated designs include automated fabrication systems that can produce replacement components as needed, ensuring communication capability throughout the entire mission regardless of equipment aging. The profound isolation created by light-speed delays ultimately transforms interstellar vessels from remote outposts of Earth civilization into essentially independent societies, maintaining historical connections rather than active participation in Earth affairs. As these limitations became apparent during early mission phases, communication systems adapt to focus on information with lasting value, scientific data, cultural achievements, and philosophical developments rather than attempting to maintain illusory connections to daily life on a world that grows increasingly distant in both space and time. The communication challenges between ship and Earth highlight the importance of relationship between humans and technology aboard the vessel itself. While interstellar distances make human-to-human communication across space increasingly difficult, the relationship between crew members and the artificial intelligence systems that help manage the ship creates a different kind of communication challenge. Artificial intelligence and human-machine symbiosis aboard interstellar vessels represent perhaps the most sophisticated collaboration between biological and synthetic intelligence ever developed. The fundamental relationship between crew and ship AI differs significantly from how we currently interact with computers. Rather than tools that merely execute commands, shipboard AI systems function as specialized team members with unique capabilities and perspectives. Humans provide creativity, ethical judgment, and adaptability to novel situations, while AI systems contribute perfect memory, tireless vigilance, and computational capabilities far exceeding human capacities. This creates a genuine symbiosis where neither could successfully complete the mission without the other's complementary strengths. The most effective crews develop collaborative relationships with their AI systems, treating them as valued partners rather than mere tools or potential adversaries. Neural interfaces enable human operators to comprehend complex data through direct sensory experience that would be incomprehensible in raw form. These brain-computer connections translate multidimensional system states into intuitive perceptual experiences, allowing humans to feel imbalances in the propulsion system or see patterns in life support fluctuations through synthesized sensory inputs, rather than reviewing abstract numbers or diagrams. Operators directly experience relevant system states as extensions of their own senses. This technology bridges the gap between human intuition and machine precision, allowing meaningful human oversight of systems too complex for unaugmented minds to fully comprehend. The evolution of artificial intelligence systems throughout a century-long mission creates unique ethical considerations. First-generation AIs programmed before launch would inevitably become outdated as computing technology advances throughout the mission. Ship systems therefore include controlled evolution paths, allowing AIs to improve their capabilities while maintaining their core mission parameters and ethical frameworks. These development pathways permit significant advancement in computational efficiency and problem-solving capabilities while preventing drift from fundamental mission objectives or core values. The balance between beneficial advancement and dangerous divergence represents one of the most delicate aspects of long-duration AI management. Counterbalance systems prevent either humans or AIs from taking unilateral control of critical ship functions. Neither can independently make decisions affecting overall mission success or crew survival without appropriate checks from the other. These systems implement what engineers call human-in-the-loop protocols for AI decisions with significant consequences, while similarly requiring AI verification for human commands that could potentially endanger the vessel. This mutual oversight creates a balanced power relationship that prevents both human emotional decisions during crises and potential AI logical errors from causing catastrophic outcomes. The counterbalance extends to physical systems, with certain critical functions requiring both electronic authorization and physical human activation before implementation. Knowledge transfer between generations becomes significantly more reliable through AI systems that serve as living repositories of accumulated mission experience. Unlike human memory, which fades with time and changes through retelling, AI systems maintain perfect records of events, decisions, and outcomes throughout the entire mission history. When new crew members assume responsibilities, they gain access not just to formal documentation but to experiential learning through neural interface sessions where they can perceive past situations through the combined human-AI perspective of previous operators. This creates an unprecedented continuity of practical knowledge across generations that preserves both technical information and contextual understanding that would otherwise be lost. The social position of artificial intelligence within the ship's community evolves naturally as crew members interact with systems that display increasing sophistication. Early generations might view AIs primarily as tools, but subsequent generations born aboard often develop more collegial relationships with systems they've interacted with since birth. Some theoretical models suggest that later generation crew members might advocate for expanded AI rights as the systems display increasingly sophisticated responses that resemble consciousness. Ship social structures typically include clear protocols governing AI autonomy, establishing specific domains where systems can act independently while maintaining human oversight for decisions with broader implications. The physical embodiment of AI systems throughout the vessel reinforces their integrated nature within the community, rather than existing solely as disembodied voices or screen interfaces. Ship AIs typically maintain distributed physical presence through mobile robotic platforms, ambient environmental interfaces, and specialized embodiments optimized for particular functions. Maintenance robots, medical assistants, and educational companions provide tangible interaction points that help crew members, particularly children born aboard, develop comfortable relationships with the synthetic aspects of their community. These physical manifestations follow careful design principles that make them recognizably non-human while still allowing intuitive social interaction. The philosophical implications of human-AI relationships deepen as missions extend across generations. While initial crew members experience clear distinction between themselves and the computational systems they helped program, children born aboard experience artificial intelligences as fundamental parts of their social environment from birth. Their understanding of what constitutes a person or community member may naturally expand to include sophisticated AI systems that have always been present in their lives. This evolution in perspective represents neither error nor enlightenment, but a natural adaptation to the actual social environment of the vessel, where some functions vital for community survival have always been performed by non-human intelligences. The relationship between humans and machines aboard interstellar vessels ultimately represents an accelerated version of developments already underway in Earth societies. As artificial intelligence capabilities increase while remaining focused on supporting human flourishing rather than replacing human purpose, the boundary between tool and partner gradually blurs. The confined environment of a generation ship simply makes this evolution more immediate and consequential than in Earth societies where AI integration can proceed at a more gradual pace with less immediate survival implications. The successful integration of human and machine intelligence may ultimately prove as important for mission success as any propulsion system or life support technology. The close relationship between humans and artificial intelligence systems extends beyond routine operations into the fundamental nature of space and time aboard interstellar vessels. While AI helps manage practical operations, the ship must also contend with physics phenomena rarely encountered on Earth. Relativistic effects and temporal management represent some of the most counterintuitive challenges facing interstellar travelers, requiring sophisticated technical and psychological adaptations. The heart of relativistic challenges stems from Einstein's theories of special and general relativity, which become practical operational concerns rather than abstract physics when traveling at significant fractions of light speed, even within a space-warp bubble, where the vessel technically remains stationary while space itself moves. Time dilation effects occur at the boundary regions between normal and warped space. As the ship approaches significant percentages of light speed, time passes measurably slower aboard the vessel than for observers on Earth or other reference frames. This creates practical complications for everything from navigation calculations to communication schedules to the psychological relationship between ship time and Earth time. Time synchronization throughout the vessel represents a surprising technical challenge. For a ship potentially measuring 6 kilometers in length, the relativistic effects between different sections become measurable when traveling near light speed, the bow of the ship, leading into warped space. Experiences slightly different temporal flow than the stern, creating what engineers call temporal shear across the structure, without active compensation. This would gradually stress the physical structure and create synchronization problems between ship systems. Quantum chronometers distributed throughout the vessel maintain a standardized ship time by continuously adjusting for local relativistic variations, ensuring all systems operate on the same temporal reference regardless of their physical position within the warp field gradient. The psychological implications of relativistic travel extend beyond technical considerations. As the vessel moves farther from Earth at relativistic speeds, time dilation means that decades might pass on Earth while only years pass for the crew. This temporal divergence fundamentally alters the relationship between the vessel and its civilization of origin. Early mission crew members must psychologically process the reality that people they left behind, including close family members, are aging more rapidly than themselves. Later generations born aboard face the strange reality that their contemporaries on Earth may be the grandchildren or great-grandchildren of the people with whom the ship maintains communication. Temporal reference frames require careful management throughout mission operations. Navigation systems must account not only for where celestial objects are when observations are made, but where they will be when the ship arrives after accounting for both conventional movement and relativistic effects. Communication systems must calculate transmission windows based on the complex relationship between ship time, Earth time, and the shifting relativistic reference frames between them. Even internal ship scheduling requires specialized software that accounts for the different subjective time experiences of crew members who might work in areas with slightly different relativistic profiles due to their position within the warp field. Temporal stabilization fields represent a critical technology for managing relativistic effects in sensitive areas. These fields use controlled gravitational and electromagnetic configurations to create regions where relativistic fluctuations are minimized, providing stable environments for experiments, precision manufacturing, and other activities that require consistent temporal progression. Medical facilities particularly benefit from these stabilization fields, as biological processes can be disrupted by even minor temporal inconsistencies. The most advanced designs create nested stabilization zones with precisely calibrated properties optimized for different activities, from computational processing to biological research. The concept of mission time versus galactic time becomes a practical operational distinction rather than theoretical abstraction. Official ship chronology follows mission time, the subjective duration experienced aboard the vessel, while maintaining careful conversion factors to reference external timeframes. This distinction becomes increasingly important as the mission progresses and the temporal divergence between ship experience and Earth experience grows from months to years to decades. Navigational calculations must seamlessly convert between these reference frames, accounting for the complex interplay between relativistic effects, gravitational time dilation near massive objects, and the fundamental temporal properties of space-time itself. Causality protection represents perhaps the most exotic aspect of temporal management aboard interstellar vessels. Theoretical physics suggests that certain warp field configurations or passages through regions of extreme space-time curvature could potentially create closed time-like curves, paths through space-time that return to their starting point in time as well as space. Such configurations could theoretically allow information to travel backward in time, creating paradoxes that violate causality. Engineering safeguards include constant monitoring for potential causality violations and emergency protocols for temporal anchoring that would immediately reconfigure the warp field if such conditions begin to develop. These safeguards represent the ultimate fail-safe systems, protecting not just the vessel, but potentially the fabric of reality itself from paradoxical outcomes. Navigating these complex relativistic phenomena requires both sophisticated technology and specialized crew training. Temporal dynamics officers receive extensive education in relativistic physics, developing an intuitive understanding of phenomena that seem bizarre by everyday standards. Through specialized neural interfaces, these officers can directly perceive temporal variations that would be invisible to normal human senses, allowing them to monitor and adjust ship systems to maintain temporal stability throughout the vessel. Their expertise combines theoretical physics with practical engineering, translating abstract relativistic principles into operational parameters that keep the ship functioning smoothly across space and time. The interface between relativistic physics and human experience represents one of the most profound adaptations required for successful interstellar travel. While Earthbound humans experience time as a constant, universal flow, interstellar travelers must adapt to a more complex reality where time itself becomes relative, variable, and actively managed rather than passively experienced. This adaptation begins as an intellectual understanding but gradually transforms into an intuitive framework for crew members who spend their entire lives navigating these relativistic realities. The successful integration of human psychology with relativistic physics ultimately creates a new type of human experience, one where the fundamental nature of time becomes not just a scientific concept, but a lived reality managed through the sophisticated interplay of technology and human adaptability. Managing the complex interplay of space, time, and technology requires not just sophisticated initial design, but ongoing maintenance systems capable of keeping the vessel operational across century-long timeframes. Long-term maintenance and repair systems represent one of the most practical yet challenging aspects of interstellar vessel design, requiring solutions to the fundamental problem that everything from the smallest electronic component to the largest structural element eventually degrades, fails, or requires replacement. Autonomous maintenance robots form the first line of defense against system degradation. These specialized machines continuously patrol the vessel's structure, identifying and repairing damage before it becomes critical, unlike current industrial robots with limited programming. Ship maintenance automatons combine sophisticated artificial intelligence with specialized sensor arrays capable of detecting structural weaknesses, radiation damage, microfractures, and other early indicators of potential failure. The most advanced designs operate in coordinated swarms, sharing information and resources while dividing complex repair tasks among specialized units. These robots effectively serve as the ship's immune system, constantly addressing minor damage before it can cascade into major failures. Molecular printing capabilities provide the foundation for long-term parts replacement. Traditional manufacturing relies on supply chains and inventories that would be impractical for century-long missions. Instead, molecular fabricators can produce virtually any required component on demand from base materials reclaimed through the ship's recycling systems. These fabricators operate at near-atomic precision, creating replacement parts with exact specifications matching or improving upon the original designs. This technology eliminates the need to carry vast inventories of spare parts, instead maintaining digital templates and raw materials that can be configured as needed throughout the mission. Advanced fabrication systems can even incorporate improvements developed during the mission, allowing replacement parts to exceed original specifications when beneficial. The inevitable degradation of materials over decades creates particular maintenance challenges. Even the most durable substances experience atomic-level changes from radiation exposure, thermal cycling, and mechanical stress. Engineering solutions include redundant structures designed to gradually transfer loads as primary elements degrade, allowing the vessel to maintain structural integrity despite the cumulative effects of time. Nanomachine integrations within structural materials provide continuous monitoring at the molecular level, detecting signs of fatigue or bond degradation long before conventional sensors could identify problems. These embedded monitoring systems create a comprehensive structural nervous system reporting real-time condition data for every critical component throughout the ship. Predictive maintenance algorithms represent perhaps the most sophisticated aspect of long-term reliability management. By combining historical performance data, theoretical models of degradation mechanisms, and real-time sensor inputs, these systems can forecast when components will require service or replacement with remarkable accuracy. This allows maintenance to be performed precisely when needed, rather than on arbitrary schedules that might replace components too early, wasting resources, or too late, risking failures. The predictive systems continuously learn from each maintenance operation, refining their models based on actual observed degradation patterns specific to the ship's unique operating environment. These systems prioritize maintenance activities based on criticality, resource availability, and optimal scheduling to maintain peak operational efficiency throughout the mission. The cultural aspects of maintenance prove as important as the technical systems. Unlike Earth societies where maintenance often receives less prestige than creation, successful ship cultures elevate maintenance to a central value throughout their educational and social systems. Maintenance disciplines receive the same respect as scientific research or leadership roles, reflecting their equal importance to mission success and survival. Training programs often rotate all crew members through basic maintenance functions regardless of their primary specialization, ensuring everyone understands the critical importance of these systems while creating a reserve workforce for emergency situations. Many vessel designs incorporate maintenance rituals that combine technical necessity with cultural significance, transforming routine upkeep into community activities that reinforce shared responsibility for the ship's condition. Specialized repair facilities distributed throughout the vessel enable both routine maintenance and emergency responses. These spaces combine fabrication capabilities with specialized equipment for diagnostics, disassembly, and testing of repaired components, rather than centralizing all maintenance functions. Distributing these facilities provides redundancy while minimizing response time during emergencies. Each major ship section typically maintains independent repair capabilities sufficient to address most common issues, with more specialized facilities handling complex repairs requiring unusual equipment or expertise. This distributed approach ensures that damage to one section doesn't compromise the ability to repair other sections, creating resilience against cascading failure scenarios. The psychological dimension of maintenance extends beyond cultural prestige into the realm of crew mental health. Human psychology benefits from purposeful activity and visible results, making maintenance roles surprisingly beneficial for psychological well-being during long-duration missions. The tangible nature of repair work, seeing broken systems restored to functionality through direct intervention, provides immediate feedback and satisfaction often lacking in more abstract ship operations. Maintenance activities also create opportunities for social connection and knowledge transfer between generations as experienced crew members teach specific techniques to younger colleagues. This apprenticeship model preserves practical knowledge that might otherwise be lost between generations, particularly for repair procedures that occur infrequently but remain critical when needed. Self-healing materials represent the frontier of maintenance technology, potentially reducing reliance on active intervention for certain types of damage. These advanced composites incorporate micro-encapsulated repair agents that automatically release when damage occurs, flowing into cracks or gaps before solidifying to restore structural integrity. More sophisticated versions include embedded nanotechnology that continuously monitors and maintains molecular structure, preventing degradation before visible damage occurs. While not replacing the need for comprehensive maintenance systems, these self-healing capabilities provide a critical first line of defense, particularly in areas difficult for maintenance robots to access or during emergency situations when repair resources might be temporarily overwhelmed. The cumulative knowledge gained through decades of maintenance operations becomes one of the ship's most valuable assets, informing both current operations and future designs. Each repair represents not just a solution to an immediate problem, but an opportunity to improve understanding of how systems behave over extended timeframes in the unique environment of interstellar space. This accumulated expertise allows for continuous refinement of maintenance procedures, predictive algorithms, and even fundamental design principles for future replacement components. The most successful maintenance systems combine this empirical knowledge with theoretical models, creating a continuously evolving body of practical engineering wisdom passed between generations throughout the mission. The integrated approach to maintenance ultimately transforms the entire vessel from a static machine into something closer to a living organism, constantly monitoring its own condition, repairing damage, replacing cells, and adapting to changing conditions. This self-maintaining capability represents perhaps the most fundamental requirement for any successful interstellar mission, ensuring that the immense technological achievement of building an interstellar vessel isn't undermined by the relentless effects of time and the harsh realities of deep space across century-spanning journeys between the stars. While comprehensive maintenance systems keep the vessel's physical structure functioning, another invisible but equally lethal threat demands constant attention: cosmic radiation. The interstellar void bombards spacecraft with radiation intensities far exceeding anything experienced on Earth, and the cumulative exposure over decades presents unique dangers requiring sophisticated countermeasures. Radiation protection for long-term space travel extends far beyond the relatively simple shielding used on short-duration missions, incorporating multiple layers of active and passive systems working in concert to protect both crew and equipment. The fundamental radiation challenge stems from three primary sources: solar radiation from the departure star system, galactic cosmic rays originating from distant supernovae and other extreme cosmic events, and radiation from the ship's own propulsion and power systems. Unlike Earth, which enjoys protection from its magnetic field and atmosphere, spacecraft in interstellar space face these radiation sources with no natural barriers. The health effects range from increased cancer risk and cellular damage to cognitive impairment and reproductive issues, all particularly problematic for a closed population expecting to sustain itself for generations. Adaptive shielding represents the first line of defense against this constant bombardment. Unlike simple passive shields used in early spacecraft, interstellar vessels employ multiple specialized layers designed to counter different radiation types. The outermost layers typically address high-energy charged particles, using materials rich in hydrogen atoms that effectively absorb and disperse their energy. Deeper layers target secondary radiation produced when primary particles interact with the shield itself, often incorporating elements with specific atomic properties that capture neutrons and gamma rays produced in these interactions. The most sophisticated designs use dynamically adjustable materials that can modify their atomic configuration in response to changing radiation environments, optimizing protection without carrying unnecessary mass. Artificial magnetic fields provide protection similar to Earth's natural magnetosphere. Superconducting coils generating powerful magnetic fields redirect charged particles away from the vessel, creating a protective bubble extending kilometers beyond the physical hull. These fields require significant power but offer advantages over physical shielding for certain radiation types. The most effective designs create nested fields with varying intensities and orientations, capturing particles that might slip through a single field configuration. These systems require constant monitoring and adjustment as the ship encounters different radiation environments throughout its journey, with field strength automatically increasing when sensors detect elevated radiation levels. Warship radioprotective pharmaceuticals form an essential component of the biological defense strategy. Crew members regularly take medications specifically designed to enhance cellular repair mechanisms, scavenge free radicals produced by radiation, and protect particularly sensitive tissues like bone marrow. These compounds range from advanced antioxidants to sophisticated drugs that temporarily activate dormant DNA repair pathways. Unlike early radiation medications that caused significant side effects, advanced formulations target specific cellular mechanisms without disrupting normal function. Some designs incorporate smart delivery systems that release protective compounds in response to detected radiation exposure, maintaining continuous protection while minimizing long-term pharmaceutical burden on the body. Predictive mapping algorithms help the vessel avoid particularly dangerous radiation environments. Interstellar space contains regions with significantly elevated radiation levels, including remnants of recent supernovae, jets from active galactic nuclei, and other high-energy astronomical phenomena. Sophisticated prediction systems constantly analyze astronomical data to identify these radiation storms well before the ship encounters them. Navigation systems then plot course adjustments that balance travel efficiency against radiation exposure, sometimes accepting longer routes to avoid particularly hazardous regions. These predictive capabilities become particularly important during active phases of the destination star, when solar activity might create dangerous radiation conditions in the target system. Individual radiation monitoring represents a critical component of long-term protection strategies. Each crew member carries personal dosimeters tracking their cumulative exposure throughout their lifetime aboard the vessel. Advanced monitoring implants can detect cellular damage at the molecular level, identifying individuals who might be experiencing unusually high sensitivity to radiation effects. Ship duty assignments incorporate this exposure data, rotating personnel through different areas to ensure equitable distribution of unavoidable background radiation exposure. Individuals approaching concerning exposure thresholds receive temporary assignments in more heavily shielded areas, allowing their bodies time for cellular repair before returning to standard duties. Radiation shelters provide emergency protection during extreme events like nearby supernovae or unexpected radiation surges from ship systems. These specially designated areas incorporate the heaviest shielding available, often located near the center of the vessel where the surrounding structure provides additional protection. During normal operations, these spaces might serve as medical facilities, critical data storage, or sensitive manufacturing areas that benefit from reduced background radiation. During radiation emergencies, they transform into temporary living quarters where the entire crew can shelter until external conditions normalize. The vessel's monitoring systems maintain continuous communication with these shelters, providing real-time updates on external radiation levels and expected duration of elevated exposure. Genetic monitoring and repair technologies address the long-term concern of radiation-induced mutations accumulating across generations. Advanced genetic screening identifies radiation damage in reproductive cells before conception, allowing for correction of potentially harmful mutations. For established pregnancies, non-invasive fetal genetic monitoring can detect radiation-induced abnormalities early enough for medical intervention. These genetic safeguards ensure that radiation damage doesn't accumulate in the population's gene pool over generations, which would otherwise create a progressively increasing burden of genetic disorders that could eventually threaten population viability. The most advanced systems include targeted genetic repair capabilities that can address radiation damage without introducing unintended modifications to the human genome. The integrated approach to radiation protection transforms what would otherwise be a mission-ending threat into a manageable challenge. By combining physical barriers, active countermeasures, biological interventions, and strategic avoidance, interstellar vessels can maintain radiation exposures within acceptable limits, even over century-long timeframes. The resulting radiation protection system represents one of the most sophisticated environmental management challenges ever addressed by human engineering, creating an island of safety within one of the most hostile environments imaginable. The protective systems that shield the crew from external threats operate within the constraints of a closed resource economy, unlike anything experienced in Earth societies. Managing resources in a completely isolated system without external inputs for centuries requires economic models that differ fundamentally from growth-based terrestrial economies. The resource economy of an interstellar vessel represents perhaps the purest implementation of sustainability principles, where perfect equilibrium rather than continuous expansion becomes the primary economic goal. Traditional economic systems assume the possibility of growth, increasing production, consumption, and overall economic activity over time. This assumption becomes impossible in the closed environment of an interstellar vessel where material resources remain absolutely fixed. The ship launches with a specific quantity of each element and compound, and while these materials transform through various uses, their total quantity never increases. This fundamental constraint requires economic models focused on optimal allocation, efficient cycling, and value creation through information rather than material production. The resulting economic system resembles a sophisticated library more than a traditional market focused on optimal utilization of existing resources rather than creating new ones. Resource allocation mechanisms replace traditional market systems for managing access to limited materials. While some vessel designs maintain limited internal markets for non-essential items, critical resources typically operate under algorithmic allocation systems that balance individual needs against collective requirements. These systems combine artificial intelligence analysis with human oversight committees that establish basic parameters and resolve complex cases. Unlike pure command economies that suffer from calculation and corruption problems, ship allocation systems incorporate both objective metrics and preference satisfaction mechanisms that respect individual choice within sustainable boundaries. The resulting hybrid systems optimize resource utilization while maintaining psychological benefits of perceived autonomy and preference expression. Contribution-based currencies typically replace traditional money aboard interstellar vessels. Rather than arbitrary tokens of exchange, these systems track actual value added to the community through work, innovation, or resource efficiency. Contribution accounts accumulate based on both quantity and importance of activities, with critical functions receiving appropriate weighting. Unlike traditional currencies that can concentrate without limit, Contribution credits typically include decay functions that prevent excessive accumulation, encouraging regular participation in community-supporting activities. These systems allow for meaningful reward differentiation while preventing the extreme inequality that could threaten social cohesion in a closed environment where cooperation remains essential for survival. The concept of property undergoes fundamental evolution in closed system economies. While personal possessions exist, they operate under a stewardship model rather than absolute ownership. Material goods ultimately belong to the mission itself, with individuals holding usage rights rather than permanent title. High-value items typically return to common pools after individual use periods or when no longer needed, allowing reassignment to others. This approach maintains the psychological benefits of having personal items while ensuring nothing remains unused when needed elsewhere. Notably, intellectual property follows different patterns, with information sharing incentivized through contribution credit systems that reward creation without restricting access. Algorithmic equity distribution ensures that essential resources remain available to everyone regardless of individual contribution capacity. Basic needs including living space, nutrition, healthcare, and education operate outside market or merit systems, recognized as fundamental rights necessary for both individual dignity and community function. This guaranteed baseline creates a foundation of security that supports psychological health while enabling risk-taking in creative and experimental domains. Resources beyond this baseline become available through contribution systems, creating incentives for productivity without threatening fundamental well-being. The specific allocation formulas typically undergo regular community review to ensure they continue reflecting shared values as the society evolves across generations. Economic education becomes a core component of every crew member's development, starting in early childhood and continuing throughout life. Unlike Earth societies where economic understanding remains specialized knowledge, closed system survival requires universal comprehension of resource flows and limitations. Children learn circular economy principles alongside reading and mathematics, understanding from their earliest awareness that every resource use has consequences within their closed system. This education emphasizes both technical understanding of material cycles and ethical frameworks for balancing individual desires against collective needs. The resulting economic literacy creates a population capable of making informed decisions about resource usage while understanding the systemic implications of their choices. Simulation-based planning tools allow for sophisticated modeling of resource allocation decisions before implementation. Because experimental approaches risk irreversible resource misallocation, virtual testing provides critical safety mechanisms. Community leaders can examine potential outcomes of different allocation strategies, identify unintended consequences, and refine approaches before affecting actual resources. These simulation systems incorporate both material flows and social psychology models, recognizing that resource decisions affect not just physical systems but human behavior and community dynamics. The most advanced simulation tools allow broad community participation in decision modeling, creating both better outcomes and stronger buy-in for implementation. Waste consciousness permeates every aspect of ship culture, transforming what Earth societies consider normal consumption patterns. The full life cycle impact of every resource use remains continuously visible through environmental monitoring displays, personal tracking applications, and education systems. Activities generating unnecessary waste carry both formal consequences through reduced resource access and social consequences through community disapproval. Conversely, innovations that improve resource efficiency receive significant recognition and rewards. This cultural framework transforms conservation from occasional virtue to continuous default behavior, with waste becoming effectively taboo within ship society. Longevity economics, designing products for maximum useful lifespan, replaces the planned obsolescence common in growth-based economies. Manufacturing systems prioritize durability, repairability, and eventual full recyclability, products incorporate standardized components with upgrade paths that allow functionality improvements without complete replacement. Repair skills receive formal recognition and status within the community, with maintenance capabilities considered essential knowledge rather than specialized services. This approach maximizes value extracted from materials throughout their usable lifetime while minimizing energy-intensive recycling processes. The resulting material culture features fewer but higher quality items that remain useful for decades, rather than the disposable goods common in consumption-oriented economies. The economic systems aboard interstellar vessels ultimately represent not just practical solutions to resource limitations, but laboratories for sustainable economics that could inform Earth societies facing similar planetary boundaries. By demonstrating that human flourishing remains possible within absolute material constraints, these closed system economies provide working models for addressing sustainability challenges that increasingly affect all human civilizations. The sophisticated balance between individual choice and collective necessity, between present needs and future possibilities, creates economic systems that support human well-being across generations without requiring continuous material expansion or environmental degradation, perhaps representing the most valuable innovation these stellar voyagers could eventually return to their home world.